All right. Hello, everyone. Welcome to another session with our memory allocator. Um, to those that are joining the stream, welcome. If you're watching this on YouTube, hope you have a great watch. And yeah, this is, if you notice, very different from the usual. Very different from the usual. It's currently 7:20 a.m. where I am, which is definitely not the common case. Usually we stream at like 6 p.m. or like 6:30 p.m. of my time. But I think I want to introduce a change. Many things in life are driven by changes, if not everything. And the morning is a beautiful part of the day. But not only that, I need to have more discipline. I need to, fix my sleep schedule and all of this stuff. So I thought of introducing this change. It's going to be, in my opinion, better because not only it is a good time to stream at, mainly because, if I stream at like 6 p.m. my time in another part of the US, it's going to be like 9 p.m., right? It's going to be absolutely late. And then Europe is even worse. Most of you guys are in Europe, if I remember correctly. So a lot of people, when I start streaming at like 6 p.m., it's like 1 a.m. for them, right? Like 4 a.m., 5 a.m., 6 a.m. So I think this schedule may be a little bit better. Once again, I need to fix my sleep schedule too. So it just works okay. Hello, welcome in the chat. Um, but yeah, I was just announcing sort of this is a new era, hopefully, so that I can have a little more discipline, wake up early, have like that sort of. Have you ever seen those videos where like the guy wakes up and it's like, oh, today we're gonna, have a nice cold bath. We're gonna wake up and we're gonna have all the attitude. So hopefully that's gonna be us now that the streams can hopefully start in the morning so that it captures um, so that it's better for everyone, right? Better for me because I have been sleeping at like 1 a.m., which is not really my usual. I usually go to bed at 10. Uh, and many people in Europe, once again, the stream times were like 6 a.m. or 4 a.m. And for those in the US, it was like 12 p.m., 11 p.m. So I think it's a change for the greater good. Um, Also, it just works okay. Like now that I see you're in the chat, how was your exploration of Elixir? I think you were the one that was exploring Elixir, right? How has that been? Or maybe I'm getting all confused and it's not actually. Oh, okay, yes, it's you. Pretty good, pretty good. I was watching an interview with the creator of Elixir, and it reminded me of what you had said a few days ago. Say I understand it well. Pretty good. Congrats. But yeah, all right. So we don't have much time. Gotta go at 10 a.m. because as well as most of you, I also have to go to some workplace. So yeah, we'll we'll see. We'll take a look. So time to lock in. Time to focus. Today, we will continue. I'm a allocator. Yes, I have like an internship to which I have to go. Um, I I don't they don't require me to like have a specific schedule. If I remember correctly, they just require me to have a certain amount of hours. So I'm pushing my sort of my my work day to accommodate for the stream, and so that's why usually many people start at 9 a.m. I want to start at like 10 a.m. But yeah. So you no, I mean, I feel like I don't like my internship like as much. I feel like I like it at the same time. There are little parts of it I don't. But yeah, I don't know. I feel like if I could have all my free time to just do these projects, it would be absolutely incredible. So yeah. Um, we'll see, we'll see. Anyways, so here we are today, being convocated by hello. Oh, sorry. I think I think I need to set up something here with my keyboard with the modifier keys. There you go. Hello, menu. Oh, there you go. Okay, this guy cannot be an option. It has to be a control. There you go. Perfect. Awesome. So now I can open the terminal. Perfect. Great. All right. So previously we were looking. Negvosa, welcome. Dude, these you you guys are like the most loyal people. That's absolutely incredible. Yeah, it's an early stream today. I think as I was telling, it just works okay. I feel I want to implement a change on things. Be a little more disciplined, especially with my sleep schedule. I have been sleeping at like 1 a.m., 2 a.m. because the streams are so late. Many people in Europe would no, when I start streaming, it would be like 4 a.m. for them or like 3 a.m. Absolutely crazy times. And for those in the US, it would be like 10 p.m., 11 p.m. So it was like bad for everyone, except for the night owls, of course. But now I feel this is a little bit better, motivates me to wake up early, to sleep well, so that I can be prepared for the next day. And for you guys, I think it's better, no? In the morning, for those in like around the California area, it's like 7:30 a.m. Those in the East Coast, it's around 10:30, and then Europe has a like way better time between 4 p.m. and 5 p.m. So I think it benefits everyone. So hopefully we can continue this. But yeah, many people are like, at least here in the US, just entering work. So I think it's a good thing, you can just have me in the background and as a little distraction. But because of that, I think our streams are going to be a little shorter. So for example, today I have to leave at 10 a.m. because I have to go to my internship. And yeah, that means we have to lock in astronomically. I have to be very efficient. So that's another motivation. Mainly because I've noticed that I'm very slow at coding. Like, we've been looking at this for, actual time, maybe like around 5 days, 1 week. So yeah, I have to be a little bit faster at coding, a little slow. The changes are. Wait, what do you mean the changes are? The changes are. That, like, you mean the changes to the code base? Like what we did last time? Let me know if that's the case. All right. In the meantime, so we're going to continue the memory allocator, I suppose. And so one of the you said you changed something in code. Oh, I didn't really change much in the code. This was sort of last time. So last time we had a few sort of things. Really, nothing much happened, right? To be completely honest with you, most of what we were doing was trying to create the testing infrastructure, which, if I remember correctly, is still the title of the stream. Yeah, creating some tests. So we're just gonna make sure that we can find a way to test our memory allocator, or at least to see what the memory allocator is doing. Those changes involved mainly creating this little file. I created a copy of what we had before, so that mm.c, whenever you call allocate, it just calls malloc, so that we can simply know if our infrastructure is right and, like, everything is set up and so on. So that is the main thing that we've been doing. Last time we basically didn't do anything. So yeah, today is gonna be the day where we do sort of most of the stuff, I hope. And to summarize, I think we have a lot of bugs in the main sort of malloc function. it is a little bit, all over the place in a sense. Um, there was the thing with the offset in the footer where, like, whenever you align something, those extra bytes go at the end of the footer when that shouldn't be the case. It should go to the end of the user section. So we need to account for that. Not only that, but here in this section of code, we're saying, oh, if the last block is free, well, go to the last block, right? And if it's free, then count that as reusable space. But then we continued the rest of the work of sort of our, flow of thoughts, thinking, not under this conditional. So suppose the block isn't free, then we end up later over here removing that block from the red black tree code, from the red black tree, right? And the red black tree contains only the free blocks. So now we're removing something that doesn't even exist inside the red black tree. Not only that, but this thing, since it's occupied, or it could be occupied by user data, by removing it from the tree, we potentially could, corrupt something in it. Here we're also expanding it despite it probably being occupied, so we would be overwriting user memory. So it's like really, really bad, which is why I created a copy and then simply made this, sort of this. So now we can think about it more carefully. But first, let's make sure that we're able to test our code. So what I introduced last time, I think, if you guys remember correctly, we were having some problems with the extension for the memory inspector, but I think I fixed that before starting the stream. So this thing over here. Oh wait, Nichols. I did investigate why flags are better put in size versus parent because all 3 pointers are given to the user in the payload. Wait, I did investigate why flags are better to put in size versus parent. Because all 3 pointers of the red-black tree plus the footer are given to the user in the payload. What do you mean? Like, wait, could you expand a little further on that? Because, I mean, we provide to the user the pointer to the beginning of the user section, and from that pointer we can access both the header and the footer. Is there something special about it? Like, in the meantime, let's run the program to see if we've done everything right. Let's see. Oh, there you go. Okay, perfect. So now, notice that we have like this little tab called memory. And so we can enter memory tab and inspect what's going on in memory. So it's very cool because thanks to this extension, we can, let me eliminate all of this stuff that we had. Perfect. So thanks to this extension, notice that now we can initialize memory, right? Then we malloc A1. And so notice that now we can visit whatever A1 is. So in this case, it's this guy, right? 0x something something. So then we can add a view for this 0x guy. Oh, whoa, whoa, whoa. Okay, I think I just need to copy that. So maybe 0x 1 2 3 4 603 1 2 3 4 5 1e 70. And then we say, oh, I want to watch, 4 megabytes of memory. And so now we can take a look at what's going on at that address. And notice when I string copy into it, now we can see what the contents of memory are, right? So it's pretty cool, pretty cool. And we'll be able to take a look at it. Now we are going to be able to read what's actually going on within the blocks and everything. And so that's better for us to debug, to figure out what's going on with the program. With that said, I think we can sort of start testing. Let's see. I can investigate Nick Vorsa as data plus footer plus 3 pointer of the user data that he requested, UA's 16 bytes plus alignment in your case that should be returned to the user pointer. Data plus footer plus 3 pointer are the user data that he requested. So data plus footer plus the 3 pointer. Let's see. So I think, let's see. Oh, Ben 1431. Could you please move the camera capture to the other side? I think it has less important stuff than the right side. Well, wait, give me a second. I'm trying to see if I can. Okay, the stream is about to lag because I'm going to enable the preview to see what it looks like for you guys. So over here, let's see. Oh, I think this camera position is a little better because moving it to the other side would imply, well, you guys don't see the breakpoints. Most of the file tree doesn't happen. Extensions. Like, because currently the right side of the screen, which is this one, has basically nothing. It's just like black area. This is gray. So, like you can see, it's just gray. So I'm just gonna position it here. But yeah, if it ever comes to like a situation where we have something maybe here positioned, definitely we can change that. Okay, let me disable the preview so that now the stream doesn't lag. Perfect. So let's see. Nightvorsa, you were saying all those are not needed if the block is allocated. So, oh, okay. I kind of see what you're saying. So you're mentioning that. So whenever we have those, the left pointer, the right pointer, the parent one, none of those are needed whenever you have the what's the name? I forget. Whenever you have allocated the block, yeah, there you go. And so, okay, back to Excalibur. Let's see. So I kind of see what you're saying. So I think that could be a good optimization, right? So if we store those bits in the size instead, so that is one of my problems, that like we cannot really store those bits in the size, because we had, well, actually, maybe we could. I think we can. Okay. Let me illustrate my thought process. So, and let me know if I'm understanding correctly what you're trying to say, Nick Volsa. So if we store those bits inside the size, that means that we can think of this entire block as being like this much long, right? Because even though left, right, and parent are taking space, right? Whenever we remove them from the red black tree, or remove this block from the red black tree and provide this to the user, we can think of this block as being this long, since once it's in use, this information is going to be useless to us because it's just no longer in the red black tree. I feel that is a very good idea. That is a very good consideration. If we store the bits in size, then whenever we're looking for a block, so suppose this block is like, remember, each of these is 4 bytes, right? 4 and then 4. Say this block is like 16 bytes of user data, or like, right, 16 bytes of extra space. If the user requests something like, I don't know, 24, right? Initially, with a current approach, we may look at this block and say, oh no, this is a 16-byte block. This does not accommodate for the user's request. But with what Negvorsa is saying, it's actually interesting because even though in the tree we see this is a 16-byte sort of user data section, it is not really that. It should be more like a 28-byte user data section. Because once the thing is, this block is removed from the red black tree, the left, right, and parent bit sort of fields of information are not going to be needed at all. And so we can just tell the user, oh, you can just start writing from here. So I definitely see that. We still need to preserve the footer because, the coalescing with blocks once they get freed. And same here. So yeah, I mean, I feel that's definitely an optimization we can make. And thank you so much, Negvosa. That makes a lot of sense. I think it is a great idea. So yeah, size is a multiple. Yeah, that's why I doubted at the beginning. I was like, I don't think we can do it with size, and then I second guessed myself. I was like, actually, I think we can, right? Because we need to keep the alignment alive. I do have to say I am not completely sure we can do it because like the size over here, right? It should actually no. Oh my god. Everything conflated, everything conspired in a favor. So wow, that's absolutely amazing. So just to introduce some context, if you remember correctly, we had always been having this problem, which is that the header was 16 bytes long. So it would be, 8-byte aligned, but the footer was 4 bytes. So now everything would be messed up because things were not naturally 8-byte aligned. But now, if size refers to the entire size, it means that our header is technically 8 bytes long, like sorry, 4 bytes and then 4 bytes at the footer, and then there's already alignment there. It's not quite that, but it's still a benefit. So like now it seems like it's a little more aligned, more naturally aligned, which I feel it's a good advantage. Let me read some messages in the chat because I have missed them. But let's see, Nick Wholesale. RPG Loads, are you from Colombia, bro? Yes, I am originally from Colombia. Currently not there, but yes, I'm from Colombia, and we're talking about last stream. So yeah. Sorry. Oof. Let's see. All those are not needed if the block is allocated. Yeah, alright, understood. Yes, footer 2. Size is multiple of 8, right? But you need to know if the previous block is free or not by storing 1 bit in the current block. Yeah, that's completely fine. That's completely fine because size, if it is 8-byte aligned, which I'm still doubting about, I'm not sure size is 8-byte aligned, but it would at least, in my opinion, be 4-byte aligned, in which case we get the last 2 bits, which is still, free game for us. Like, we need 2 bits at least. And so 2 bits is more than enough. You don't need footer 2. Just so 1 bit in the current block in size. Size will have 3 bits. So we do need the footer because I think it goes back to what we were saying before, where suppose this block is allocated, right? This guy gets freed, so he gets freed. And then later this guy on the right gets freed too. When he gets freed, he wants to know if the block to its left is free and the block to its right is free. So first it checks on the right. If it's free, then merge them together. If not, then leave it alone. And it's going to do the same with the left, right? If it's free, merge them together. If it's allocated, then don't. It could detect if it's free by looking at 1 bit. The problem is that it not only needs to know if it's free, it needs to know who that block is. So it needs to know how to travel to the header of that block so as to modify the size information on the header. So it needs to travel like all the way back to the beginning of the header so that these 2 blocks can merge. So we still need the size to be there. Because although 1 bit would suffice to know whether it's free or not, it doesn't suffice to know where the header is. And since we only get a pointer to this block, we don't have any information about the block that's to our left. But yeah, just still 1 bit in the current block in size. Size will have 3 bits. Yeah. Well, assuming size can have 3, but yeah, I think 2 is going to be enough. Put 1 bit in its block to know if it's previous free or not. But yeah. So I think that is the main problem. That if we go to our left, we can detect whether or not it's free, but we need to know the actual size. You need size only if it's free to merge, but not if it's allocated. I agree. But okay, wait. I think what you're saying may have value. Okay, I see. So we're sacrificing a lot. So not only are we so yes, we don't really need the size when the block is allocated, right? So if I think what you're suggesting is when the block is free, all of the metadata looks like this. But if the block is occupied, then we only need 1 bit over here. If it's allocated, then we can only tell with this bit that we don't need to do anything. And if it's free, it means that it's going to have the metadata, and thus we're going to be able to access the size, right? I think that's what you're saying. I would be willing to say that makes sense, but let me think about it carefully. Let's see. If you're allocated and then you get freed, how could you recover the original size? I think you could perfectly still do it because, yeah, I think that makes total sense. Yeah. Yeah, no. The BIC is in the next block. So this is my block, right? This one. And then we just look to the left and take a look at that bit. I think that makes sense. I think I'm willing to say yes. I'm willing to say yes. That that makes a lot of sense. The bit is not in the footer. Oh. What do you mean? I think the only reasonable place for it to be is in the footer. Wait, maybe I'm not understanding what you're saying completely. Let me know. But I feel these are great optimizations, actually. I think we can definitely implement those ideas. Let me know what you mean by saying that the bit is not in the footer. Because what I was thinking is we have the bit here on the block that's like right next to us. And so when we get freed, we can just take a look at that blocks, whether or not it's free. Nothing in the footer. So that becomes a problem, right? Because if you need to know about, let me think. I guess if we treat this as some sort of linked list where I am providing in my header the information of the previous block, then in that case, we should be able to... Okay. So just to summarize what we've been looking at, and welcome to the new viewers that are tuning in. We're working on our design. Nick Volta has proposed some very good optimizations, and so now we're evaluating like how to implement them and if we want to implement them. I think we want for sure, but now we're sort of converging on what the idea is. So you're saying that, okay, what I was saying previously, just to put you guys in context, is after sort of my interpretation of Nick Volta's idea was every block in its footer contains a bit, a single bit, that says whether or not it's free, right? So now if you have a situation where 2 blocks are next to each other and they're allocated and they're suddenly freed, then what's going to happen is this block gets deallocated. It looks to its right, sees this guy is occupied, looks to its left, sees that guy is occupied or something like that. And then when this guy is freed, he looks to his right, checks the header of the next block, whether or not it's free, and then goes back, and it only needs to look at the footer and say, okay, is it free? If it's not, then we have no business to do here. If it is, then the metadata is going to be there because the process of freeing implies refilling the metadata, right? And so that was what I was saying. I think what Negvosa is saying is something a little bit more aggressive. And that is the next block is the one that stores your information in its header. So if we are to think of like these three blocks that we have right here, I know it's a little bit difficult to keep track of it, just with me, you know? This block in Negvosa, let me know if this is what you're thinking. This block stores the information of whether or not the previous block is free, right? And so what that does is over here, I'm gonna erase all of the drawings we've been making for what feels almost like an eternity. Let me delete all of this, all of this, all of this, all of this, all of this. There you go. So I think what Negvosa is saying is we let the next block store the information of ours, right? And so that way, suppose we have the same situation, right? This block is allocated. This other block is allocated. And this other block is also sort of allocated, right? So so suppose that this one is freed, right? This little guy is freed. Oh shoot. Wait. Okay, I think let's do it like this. So this one's allocated. This one is also allocated. And this one's also allocated, right? So all of them are allocated. And you can imagine that maybe this one on the right gets freed, this one on the left gets freed. When this guy gets freed, he can still know everything about its fellow patriots, right? Because to the right, he just needs to look at the header. The header is going to tell it the size of this new block, and so now it's going to be able to merge. And if it wants to look to the left, right? So if this block has been freed, the metadata is going to be there. But if the block is occupied, that metadata is no longer there. So how does it realize whether or not that block is occupied or not? Well, remember, the next block stores the previous block's metadata, which means that I already know what this guy's status is, whether or not it's free or occupied. And so one way or another, we can figure out what's going on with the blocks to our sides, which I think is a brilliant idea. Because it means that we have reduced the memory usage to only 8 bytes. It's absolutely insane. I think it's one of the greatest suggestions. Yeah. So thank you very much, Nick Woolsey. It's an excellent idea. And I think it's what we're going to do for sure, because yeah, pretty good, guys. Let's go. So let's do that. Oh, I just want to delete that. Oh my god, this arrow is so annoying. But perfect. Okay. Yeah, I think that is a great observation. So yeah, I think we can implement that. Let's see. No ideas is a question I say I implement part of it. Okay. Yeah, I mean, I'm trying to stay away from AI just so that we can think about it ourselves. But yeah, thank you for the contribution. Okay, let's try to think about all of that, and let's try to think about how all of this affects our current code base, which I think it's not going to be that much of a change because remember, this is the reason why I pushed so much to have these functions rather than the thing sort of interacting with the header by itself. And it's because now, if we want to access things, right, now we can just, instead of having the free bit in the parent sort of section, we can just have it in the size, and so nothing is going to change in a code base. So that's absolutely awesome. So I think we need to. There's a couple of things that we need to have very clear. And it's gonna be over here. So things that I want to be clear about, and is that size stores the size after sort of the block, or stores the size if the block is to be provided for allocation. So what I mean by this is size, instead of storing sort of this little section of what we are, where we so far have been calling user data, which I think should now have a different name. Size stores not this size, which is what we've been storing, it stores this size. Okay? For that reason, it may be a little confusing sometimes. So you just have to keep that in mind, right? Size refers to whether or not, to the size of the block if it were to be provided for allocation. So there you have it. That's going to be size. Size, it's also going to be sharing room with the free bit, and it's also going to be sharing room with the color bit, I imagine. There's not much of a need to have the color bit be with the size, because the color bit could just live with the parent, since, color is only important for a free block, and when a block is free, we get access to the metadata. But it's good to just have one field where all of these little bits are present. So I think this is the way we're going to plan it, right? Size is going to get thus the sort of its full capacity of expression, since we know that size will hopefully be at least 4 byte aligned. I think that's definitely the case. And free and color, I think, well, no, it is for sure the case. Like, size will be 4 byte aligned. So, yeah. And free and color are just going to occupy the last 2 bits of size. So I think that's a great idea. We need to take a look at what things change in our implementation. So, first of all, the header stays the same. Footer stays the same. It's still the same footer, it's the same header. It's just that things change whenever something's allocated. And I need to make a remark here that, so something very important, which by the way, I think, let me know if you guys can see the red text now. I spent 2 hours yesterday, no, 3 hours yesterday, trying to set it up. And I think I succeeded, although I'm not sure. Like, I looked at recordings and everything, and it seemed fine. Yes, we can. Yo, let's go. Okay. So, very important. We actually need to implement, free refers to the previous block's status. So I think it's good to implement, something like p-free or like previous free, or yeah. Yeah, pref free. So I think pref free is what we need. I must be color blinded. I can see it clearly. Yeah, so you can you can see the red like clearly in the black background, right? I hope. let me know. But yeah, thank you, Ben Ben, for reporting that. Yes, you can. Uh, yeah, I mean, in same with the breakpoints. Like, I think we have to appreciate how beautiful this is. Like the breakpoints are like bright red now. So thankfully, or hopefully, you guys can see it. I increased display intensity. Okay. Um. So yeah, very important. I think we only need these two pieces of metadata. I'm willing to say we do not need a free, so something that indicates whether we as a block are free. Although let me know. Maybe I'm completely wrong. But yeah, so over here, over here, we're gonna keep taking a look at this. So size stays exactly the same, left the same, right still the same, parent is still the same, setting the parent is the same, but now we need to, sorry, it doesn't stay the same. So size now it's going to store 2 bits at its end, which means that this code that we had for the parent is now going to instead go for the size. So here we want to return from the header, right? I want the size, sorry, from the header of this block, I want the size field, and I want to return, you know, only the mask that excludes the last 2 bits, right? Perfect. Okay, this is gonna be a problem. It's gonna be a problem because I didn't want to create a function to set the size, since like we shouldn't be setting the size whenever we're working with a block unless we know what we're doing, because it's very likely that we will get confused at some point in time and we simply say like, oh, we need to expand this block, you know, set the size of it, and then, you know, pack your bags and let's go. That's not the way it works, right? Because changing the metadata is not going to change the actual reality that your block has not yet expanded. So I think we just need to be careful. I'm going to just define in that, right? Guys, it's 7 minds right now, 7 minds looking at the same code. If you ever see me write something that's really free, like really bad, tell me, okay? If I'm calling set size, pretending like the block just expanded, just let me know. But hopefully that won't happen. And to set the parent, sorry, not set the parent, but set the size, we simply need to access in the header of this block, of this block, of this block, of this block, the header of this block, we need to access the size section, and we need to make it be, so first we zero out whatever's in those first positions. So we zero out whatever is in, sorry, this should be an and with 0b11. Yeah, there you go. And then we with whatever we have, or whatever we want to set the size to, which means we need to also accept a size parameter. So uint32t and then size. Perfect. And this size is going to be odd with whatever size is. So I think one thing we can do is assert every single time that size modulo 4 is equal to 0. So if we ever have a size that is not 4 byte aligned, this thing is going to complain, and loudly, right? So that would simplify kind of everything, because if it's 4 bytes aligned, then we actually know that the last 2 bits are 0. So ORing it would, you know, generate no trouble. So yeah, left, set left, right, set right. Parent, I think now what we should do is in the declaration of a struct, instead of referring this as size, we can do something like size, prev free, and color. Now, you may be asking if this is not a good name, right? It's not a good name because it's very confusing, right? I don't know what this means. somebody else from another code base may be confused by what this is. And so I think that the reason why I want to do it this way is so that it looks so confusing that we are sort of motivated to not use it, right? So what I mean by that is we don't want to have somebody open the header of a block and then setting the size, right? Because that would be really bad. We would get rid of a bunch of metadata that we need. If we name the field SPFC, right, it's going to be really difficult for us to be like, oh yeah, I know what I'm doing. Like when you look at this, inherently you say there has to be something fishy. And so now you remember, oh, size I actually need to set with the set size function, right? So it hopefully is like an implicit deterrent, since we cannot, guarantee that struct won't be modified. It's just the way things are. But yeah, it's psychological traps just to keep our feet on the earth. So now that we have this, I think we can change the name of this to what we had determined it to be, SPFC. And we now need to change this member to simply be parent, right? So parent is now free. Parent no longer carries the burden of all of its children, and thus we are happy. So parent should be equal to parent. There you go. And so now we can do parent here. Well, color is going to change. Yeah, all of these are going to change. So for color, right, what we want to do is bk header. So for the header of this block, right, what we want to do is we want to access the color. And the color, I'm willing to say it's going to be the last bit, right? So we're simply going to return this and it with the last bit, right? To set the color, we simply need to enter that block's size, like SPFC field, and then all this with whatever color is, right? So color is an enum. We simply convert this to whatever size is, so it should be a UN32T, 32T, and that should be completely fine. Yes. So now is free. It's going to be that second to last significant bit, least significant bit, and so it's ended with this. And to set the free, I think we can just, we first. I think that's something that we forgot to do with color. So we enter the header of this block, and then after that, we need to end this with the negation of whatever 0b1 is. And so we zero out the color field, and then we set it. And then the same thing needs to happen here, right? Where we zero out the second to last least significant bit, and then we set that second to last least significant bit. Awesome. Perfect. So this is going to involve a lot of changes too, because so I think we're going to dots are clear, previous three, size all equals, and then dot 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 is a bug. Why? I mean, of course. I mean, we had that line before. For some reason, I deleted it. I don't know why. But we need to apply the same reasoning here, where we need to end with the negation of, not the negation, sorry, we need to end with 0b11. And then we all with the size. I think it's perfect. So I think this is just what we need. Perfect. So one thing I want to do is I want to test these functions, like at least have little tests so that we can live a more peaceful life. So I think we can simply say test block. I think, what did we call them? And we called them something like block access functions, like block member variables, block member variables. So let's just test that real quick. I know, a little annoying, I know. Tests, worst thing ever. Line 44, you say? Is something wrong with line 44? I think we're fine with it. Let me know. But if we want to test the block member variables, something we can do is simply create sort of our own little version of a block, and then we're just gonna malloc, I don't know, size of, size of the header, so block header, and then size of a, well, actually, most of the functions assume that this is going to take place inside of the, the allocation and whatnot. So I think we'll just have to trust them for now. Yeah. So, okay, I'm gonna drink some water. Okay, so that is our current block member variables, which is just like present as functions. And what we can do now is take a look at the places where size was being used. I think we're fine. Okay. So when we partition a block, this is one of the places where we need to access the, the raw pointer for, or like the raw size field in the header. So instead, we can, let's see, so what does partition block do? It calculates the total space of the block we want to partition, calculates what's going to be the size of the block in the left, and then we are left with something in the right. Once that total space in the right, if it is, it has to be at least able to accommodate for a block of size 0. If that is the case, because that is the responsibility of the caller to make sure that that's the case, that the block can actually be partitioned, then we can update the left block, right? So we would have the header, and this is exactly where things happen. So now that we have this big block, right? We want to partition it. We know the total space. Many of the calculations are going to be offset by everything, right? Because the size of the block, it's actually the size of everything, including the metadata, except for the size itself. So I think we need to clarify that. I'm just going to write it down here. I think it's just too important to miss out. So let me actually include the function signature for set size, which was not present in the header. Over here, set size. And there's going to be a next then. Oh, well, why did we go back to the same file? What the hell? Okay, here. Perfect. So void set size and everything. And this guy needs to be an extend void, right? Awesome. So now that we have this, it's definitely beneficial to have that remark with the doxygen. Something like brief stores the size of the block. I think we put it into words in a very good way over here. Stores the size if the block is to be provided for allocation. Yeah. Store the size of the block if it were to be provided for allocation. Right? So now that we have that, I feel it's going to be a little clearer, I suppose. Not sure. But it is the most we can do. We just have to be a little bit, better with our usage of size. So let's reevaluate everything. So here I have a copy of the file so as to not lose our previous code. I am, for the sake of not only simplicity but avoiding bugs, just going to delete all of this, okay? Except for the assertion. So let's go through this logic again, since we changed the way blocks work, so that we can actually make sure that everything's done correctly. And one thing that I actually realized I missed, when we are talking about seeing whether or not a block is free, we have special cases. Oh, this is an copy, sorry. We have special cases. And by that I mean, like, if you want to know whether or not this block is free, you cannot look at this block's header. You need to look at the next block's header, right? So that since the next block stores the information about the previous block being free, then we need to do that, which is the reason why I was mentioning, like, we do not need current free. We don't really need to update that, right? Since we already have, like, the next block already stores that information. I mentioned special cases because if we want to know whether or not the last block is free, then there is no block after the last block, right? Which means we're going to have a block at the end that just is never used. Pref free, curve free must be on the same header at the same time. So what I'm saying is we could just save curve free. So my only problem with like, if we save the space from curve free is that it's only 1 bit, right? So I think we could store it. Size, nonetheless, is not the one that would store it, is the problem, right? So size is 4 byte aligned, at least, right? We cannot guarantee it's 8 byte aligned. And in fact, I don't think it will ever be. I think it will always be 4 byte aligned. So now we need to store the current free and the previous free information in one of the other metadata fields. So if we think about it, let's see, which one do we always need both of those in the header? Or can we store one of them in, say, the footer or something like that? So if we store the information of pref free, because currently what is holding me back? What's holding me back is if you have, like, the last block over here, you don't have a pointer that tells you, like, oh, this guy right next to me is free. If we store that information inside the header of each block, then we're not going to have a problem, because size can hold at most 2 bits extra that we have to spare. And we're already using those. We're using one for the color and one for the previous free. So I think what we can do is we can keep color in the parent, because color is going to be relevant only when the block is free. And then we can keep size be current free and previous free. I think that's the change we want to implement. So let's implement that. Yeah. So I'm not going to expose those in the interface. And by that, I mean we are still going to keep our functions the same. I don't want to create a function that is like block is prev free. I just want the user, which in this case is ourselves, to be able to just say whether or not a block is free and not worry about how the underlying, bits are being moved around. So we're gonna have this name to SPFF. So previous free and free are the things that are being stored here. And for that reason, we need to modify our actual implementation of the functions, because now size just simply changes its name, right? And for color, there's a change. Color needs to coexist with the parent. So now we need to make those updates to the parent. So here we have the block, the block's parent, right? If we want to obtain this information, we need to return. Well, actually, I think we can just return this with the negation of 0b11. To set the parent, we actually need to say, oh, I think we can all this, right? Can we not? Yeah, no, I don't think we can. So we can enter the parent, and I think we can once again call this what it was before, parent color. And so parent color now is equal to, everything being blacked out. So 0b1. And then to set it, we simply OR it with whatever the new parent information is. And for this field, we simply need to return the negation with the one last bit. I think that's fine. Perfect. So now the color, we're going to enter the header to obtain the color. We want to enter the parent color field and then get only the least significant bit. Perfect. To set the color of our block of memory, we want to enter the parent color field. We want to actually do something like, the negation of that. The negation of that, so that everything is once. When we end it, the parent is still going to be there. And then the color gets to take place by ORing this with whatever was already present. Since parent is a heap pointer, we just convert this to a heap pointer before. Because remember, the color is an enum. It's stored in a new int8. So we just perform the conversion so that the data types are the same. I don't think that's completely necessary, but it's good to do. The block being free, it is still. So for this one, we need to perform a little bit more modifications. Thunberg, holy what do you mean? So, yeah, welcome to the early stream. Welcome to the early stream. I think this is going to be the new schedule from now on, because we need to fix our sleep schedules too. But yeah, as I was saying, so whether or not this block is free is going to be present in the least significant bit, right? So previous free is going to be the second one, and then free is going to be the least significant one. And then to set this block to be free, we need to not only set current free, but also the next block's prev free, right? So what we need to do is block header, right? We access that block's header. We access the, size, previous free and free, little guy. And so what we need to do is we need to set current free. And to set current free, we set the least significant bit. So now we say, okay, let me set that least significant bit. So I'm actually going to kill two birds with one stone. Actually, no, I think that's better. We AND it with the negation of this, so that only the least significant bit is now 0. And we finally, after that, the block, right? Then SPFF, we OR it with the actual is free value, right? And now we need to go to the next block, and say something like, you know, the header of the next block, which I think we can just, next block of a block is not a function that exists yet. So I think we can just, I'm actually going to just say block member variables. And then we can have this be something like block, what? Block, family members. I'm not, I'm not sure what to tell you, right? The one that's on the left, the one that's on the right. What do we call this, right? Like these functions, we can categorize as like block member variables. That makes sense. But what category could we provide to a function that is like, next block, previous block, like block access to what? My sleep schedule is good. That's why I'm a shitter programmer. Yeah. Oh my god, Jasper's rating with a party of 68. Oh wait, is this Jasper the Jasper we were talking about last time? Oh my god. Dude, is this a dream come true? Welcome everybody to the stream. Here we're coding a memory allocator. I mean, I don't even know how to uh, yeah, welcome everyone, and thank you so much, Jasper, for. Yeah, it's a dream come true, bro. Hello. Yeah, I don't really know what to say. Thank you. Yeah, so welcome everyone. Okay, I need to sort of set. Welcome everyone to the stream. So, and today we are working on coding a memory allocator from scratch, and we've been working on this for around, actual time a week. We started like 2 weeks ago, but I've been really sort of on and off from the project, unfortunately, because I have other obligations. But yeah, so this is a space for everyone to learn. I know Jasper, you're a little bit more technical, and maybe the entire audience, maybe you guys. I think absolutely everyone present in the stream usually knows a lot more than what I know. I'm still someone in college, right? I'm still in college, so I'm still learning, but I'm really interested in low-level programming and all that stuff. And it's the reason why we are coding a memory allocator from scratch. Before this, I had absolutely no idea of how memory allocators worked. And I feel like one of the best things you can do to learn is, learn through actually doing stuff. And despite this seeming like a rather, sometimes maybe scary challenge, it's been proven to be very entertaining. So if you want, hang around, put us in the background, because sometimes like I recognize that maybe, actual coding is not as fun. Oh, sorry. Seeing someone code is not as fun as coding the things yourself. So yeah, feel free to hang around, to provide any sort of input, to let me know if there's something I'm missing, because once again, not an expert, so many times I make a lot of mistakes. But yeah, feel free to hang around. So for some context on what we've been doing is we've been planning a memory allocator throughout these weeks or throughout these days. We landed on this sort of design. Neg Vorsa, which is one of the chatters that has stayed with us from like the beginning, has suggested a lot of ideas on some optimizations we can make on the design, and we're currently implementing that. So currently we're taking a look at our block member variables. This is also my first time coding sort of seriously in C. Usually I code in C++. So yeah, many things about the language. We are creating these block member variables, to obtain the size, left, the color, etc. And what we are trying to do is we're trying to perform a lot of optimization. So currently, the way things look right now is every single memory block is going to have this sort of structure, right? We're going to store in a memory block the size, right? Both in the header and the footer, the user data, of course, and you may be asking, what is this, right? Well, this are sort of the metadata necessary to support a red-black tree embedded into our memory allocator, right? Why are we using a red-black tree? Because, well, we need to support a policy for allocation, some sort of policy. That could be worst fit, best fit, next fit. I decided to go with best fit. It seems to be, one of the reasonable ones and also one of the more challenging ones. So that's good. And when it comes to best fit, you need to have efficient search. And of course, where is the first place our mind goes? It goes to precisely binary search trees. The problem with binary search trees is, as many of you know, it's very possible that a binary search tree ends up being completely unbalanced and it just becomes a stick, or right to the point that things don't take log n of search. They start approaching more the linear factor. So an alternative to that is just using alternate binary search trees or sort of improved binary search trees, which are AVL trees and red-black trees are sort of the main ones. I've usually always used AVL since it's a little bit easier. Red-black trees I didn't know anything about before starting this, so we spent like a first 4 days coding our own red-black tree from scratch, whose code you can see over here. Right, so if the tree is empty, this was hell. This was, if anything, one of the worst. Like, the amount of cases that you need to have for a red-black tree is something extremely insane, right? Case 3, if your sibling is black and its two children are black, or if the child that's farthest from you is red, but the one that's closest to you is black, and your parent is black, then rotate the tree. So it was a little tedious. We learned a lot though. I think the rules of a red black tree in all of the cases are ingrained in my memory, and hopefully in everyone's too. So yeah. And the reason why we chose red black trees is because red black trees, in order to get implemented, they only need one bit of extra information. So they need the left child, the right child, the parent, and the color. And color is only one bit because it's either red or black. Now you may be thinking, why do we need a parent, right? Maybe as we traverse through the tree, couldn't we just keep a memory of who we've been visiting and thus know who the parent is? I would say yes. The problem is whenever we need to use the red-black tree is when we are talking about the free blocks. So the red-black tree, once again, stores the free blocks so that we can search on that tree for a free block that satisfies the user's request. And the problem is when the user calls free and then they give us the pointer that we previously provided to them, it means that we need to, sort of remove we need to have random access in the tree. So if you give me a node in the tree, we need to be able to remove it, right? So it's not like they give us a key and then we need to look for that key in the tree. They just give us the node that they want to remove. And thus we need random access support, and that implies having this parent field, right? So that's the reason why we've been using red-black trees. And yeah, so an optimization that Nick also was suggesting is if we have all of this metadata, right? It's not like this little piece is the only thing that can be the user data, the thing that stores user's data. We could store user data inside of basically all of the block. You may be asking, how is that possible? The idea is whenever you provide a block to the user, you no longer need this information. Why? Because, well, if block is allocated, it means it's not free. And if it's not free, it means it's not in the red-black tree. So we don't care about that, which means we can actually expand the amount of data that we provide to the user by a lot. The way we can perform that optimization is simple, right? If it's allocated, we just don't care about it. Now, we also have this footer, which is the size. And the reason why the size is duplicated on either side of the memory block is because when we are dealing with frees, there is something called false fragmentation, right? Where you have a block over here, maybe it's allocated, and maybe this one's also allocated. If you free this one and then you free this one, right? The program, if you don't merge these two blocks together, our allocator is going to think, oh, I have a block of size 12 and a block of size 12. If the user asks for 24 bytes, the allocator is just going to see these two things as separate, despite the two of them being next to each other and the two of them being free. So what we need to do is whenever a free happens, we need to take a look to our left and see if that guy on the left is free. And if it's free, we merge together with it. And then we take a look to our right, and if that right is free, then we also merge with it, right? So the way we need to, or the things we need to support that is to have a size here at the footer, because if I'm taking a look at the block on my left, I don't know where the block's header is. Maybe this user data is 20 bytes long. Maybe it's 40 bytes long. Maybe it's 30 bytes long. We don't know. So the way we can tell is just by including a size footer. So now I know that the footer is always going to be there. I take a look at the size. Once I know the size, I can jump to the header and update all of this metadata so as to merge these two blocks together, right? Now, Negv also suggested that, well, we don't really need the size footer either, right? There is an optimization that we could make where we include a single bit that tells us whether or not this block is free. If it's not free, we don't need the size data at all because we cannot even merge with it in the first place. And if it is free, then it means that at some point in time, this block was freed. So we reinstalled the entirety of the metadata, right? So it's like part of the responsibility of free is to reinstate the left, right, parent, and column metadata, but also the footer's metadata, which means that we can save even more space. Now, you may be saying this bit over here is sort of making things ugly because now we're giving like 3 extra bytes to the size, to the amount the user has, but like 3 is not a byte aligned. It may, cause some issues with alignment. Could we have everything for ourselves? And the answer is yes. What we can do is instead of storing the bit on the footer, we can store it on the header of the next block. So the header of the next block is going to tell us whether or not the previous block is free. That way, whenever I need to check to my left to see if that block is free, I already have the information. I already know whether it's free or not. If it's not free, then I don't even need to look at it. And if it's free, then it means that size was at some point in time reinstantiated. So it means that we pass from a previous design, which was this, right? It was this whole thing with the metadata, and user data would only get this section here, to this, which is absolutely fascinating, right? It's I think a very, very good suggestion. And we are now sort of modifying all our functions to accommodate for this new design, right? So as we were saying previously, we have here the size of the block. We simply, also to introduce some context, we're storing everything in a struct, right? So a header struct looks like this. You may be saying, why are these fields named so weirdly? It's because we, inside of the size, want to store more information. So we not only want to store the size, we want to store the previous free, so whether or not the previous block is free. And we also want to know whether or not we are free, right? The reason we can do this is because every single block is going to be a byte aligned, right? Size is going to be 4 bytes, which means that if you look at this metadata, all of this is, if I remember correctly, 4 byte aligned. So in the end, everything ends up being 8 byte aligned. So size, since this whole section is 4 byte aligned, that means that the last two least significant bits are not going to be used at all, right? Since it's 4 byte aligned. And they're always going to be 0. So we can use those last 2 bits to store whether the previous block was free and whether or not we are free. So that's exactly what we're going to be doing. And that's why you see, size. To obtain the size, simply grab that field and then, and it with the negation of this guy, and so on and so on and so on. The reason why they're named like this is because we want this to be obscure enough to the point that we as the programmers don't want to use it. Because you're not supposed to say, if this was named size, right? Saying something like, block header, then passing in the block, and then saying something like size is equal to 10, this would be completely incorrect because you would get rid of the metadata that we are allegedly storing. We instead want ourselves to use the block set size function. So in a way, it's a psychological effect that if we have a name that seems like it's not supposed to be used in the wild, we get a little bit, deterred from it. So this is the reason why maybe you have some different suggestions. Let us know. But yeah, we have here the size of that block. Then we're going to set the size of the block, through bit manipulation and stuff. I think we were writing. So yeah, here in the parent. In the parent, we're also going to store the color as the least significant bit. So we access the PC field, parent color field, and we end this with the negation of 1, which would be ones all over except for the least significant one. To set the parent, yes, this is correct. To get the color, we'll get the least significant bit of the parent. To set the color, we preserve the parent, leaving the least significant bit as a 0. And then we OR this with the actual value of the color, which is either 0 or 1. Now, whether or not a block is free is something we can tell by taking a look at the least significant bit. So remember, it's going to look something like size, and then whether or not the previous one is free, and whether or not we are free. So we can know whether or not we are free by just looking at the least significant bit. To set a block as freed, we need to go to a header, right? Set the least significant bit to free, but we also need to go to the next block and tell the next block that its previous one is also free. And so now we need to implement a function that's something called next block, previous block. I'm just going to call it block family members. Once again, not sure we have a better name for it, but let's just call it block family members. And we can simply have, extern, we're going to return a heap pointer to something, and then it's going to be, calculate the next block, right? So the next block for whom? Well, the heap pointer of the block. So give me the block you want to know the next block of, and I'll precisely provide you the next block. So the way we can go to the next block is we take a look at our own header, then we take a look at our size, and then we skip or jump that amount. So I guess we could just do block plus whatever the size of size is, right? Which should be a year in 32T. And then after that, we add whatever my size is. Yeah, perfect. So that seen in the Excali draw should be something like you pass me a pointer to. Ooh, we've been drawing a lot. So we get a pointer, a heap pointer to the block whose next block we want to discover. So say this one, and now I want to know who is my next block. So I'm going to take a look here at the beginning. Then we're going to say, let's jump over the size. And then the size is going to be representing this whole size, right? The size of this whole thing, sort of the effective size that the user is going to get. And thus we jump by that amount, which means we end at the beginning of the next block. We end in the first byte of the next block. And so that would be the way to access it. Um, yeah, I think that's totally fine. And so now we can say in the block header of the next block, we want to set that second to last least significant bit. So we're gonna make everything be ended with 1 except for the second to last least significant bit. And then after that, we're able to say, oh, sorry, this would be in the SPFF member variable. And then we can access also the next block, and then our block. And then of course we access that same field just to OR it with the is free, right? Just shifted by 1 to the left. And I think that's more than enough. Perfect. Negosa, inline func or move it in a .c. Oh yeah, you're right. For some reason I included the, yeah. I marked it as extern with that intention, so not sure what happened there. But yeah, so I think we can have the block family members over here. Over here. And then copy that implementation. We have a void next block. Sorry, not a void. It returns a heap pointer. Let me correct that. So give me the heap pointer of the block, whose information you want to know, and I'll return to you the heap pointer for that. And now in the header, we need to update the return type to, I think it's correct. So heap pointer next block. I think the signatures are the same. Yeah, perfect. Awesome. All right, so now that we have this, I think, is the logic correct here? Let's see. We negation and then we or yeah, I think we're fine. So this way we have updated everything to reflect the optimizations. Pretty good. So now I think something that we can do is take a look at our logic and how it changes. One of the things that worries me the most is the red black tree. So did the red black tree's logic change? And my answer would be no, because we made sure that it would only use the member functions, and those member functions have definitely not changed in behavior, at least, from the perspective of an outside observer. So I think we're completely fine with this, right? Yeah, we always use BK right, BK left. There's nowhere we're using a header, and we made sure of that in last stream. So yeah, I think we're fine with the red black tree. If anything, we're just gonna discover that with the testing. Okay, so now we move on to the actual nitty-gritty of the memory allocator. Once again, we had some code from previous sessions. We had implemented Malloc. We had like all of this. It had some errors and some bugs. And given that we now have restructured sort of the design of our blocks, we can sort of use this opportunity to rewrite Malloc and be very careful about the things we write it down. So let's see. So I'm not going to take reference on that. Perfect. So one of the most important things that we're going to need to implement is this function, partition block. Our memory, in general, is going to look something like these blocks over here, right? I'm so sorry, all of the drawings are like absolutely chaotic because of our previous sessions, where I was drawing circles and arrows, so don't worry. I know. A little disorganized, sorry. But it is what we have, So we can think of memory as like, the usual strip, right? Suppose each of these blocks is like 4 bytes long. It is the usual strip, and what we can do, right, if we think of a heap this way, is the heap is at every point in time going to be covered in blocks. So if this is the size of the heap, and the heap is initially empty, then we're going to have a big block that's just of size 52, and it's free. Now, once the first allocation comes in, say somebody wants to allocate to Malloc 12, and the reason why this is called Malloc, nobody knows, right? It's just the name I decided. Yeah. The new Malloc, maybe. Not actually Malloc, maybe. You know, it's just Malloc. It's sort of the copycat of Malloc. So if a request called Malloc 12 comes in, then what we're going to do is we're going to grab this 52 block, this block that's, you know, a free block of 52 bytes or whatever. We're going to split it, or maybe, you know, over here. We're going to split it so that now it's two blocks. One block of size 12. 12. I should have drawn the line over here instead of there. There you go. 12. And then we're going to have a block that is of size 40. Right? These numbers don't add up, right? Because we need the metadata and stuff, but you understand the point, right? So we need to perform these partitions constantly. They are the way new blocks come into existence. So we're going to pay attention to this function and we're going to write it very carefully. Currently, I think we also had this partition worth it. I'm going to delete the contents just so that we're not biased. And let's see. So what do we need to do to implement our dream? You know, first of all, we should only partition blocks, and this was sort of a divergence in our thinking. We need to partition blocks that are free. Right? We don't want to partition blocks that are being used by the user because that will, you know, generate corruption and all that stuff. You may be thinking, why do we have this assert here? Because that assert says only call partition block with things that are not free. And although counterintuitive, it sort of makes sense, right? The reason is when we partition a block, right, we're going to have to, you know, not only partition it, but this block's information is going to change. More specifically, its size. What that means is that now the block may occupy a different place in the red-black tree. And same for this guy that just came into existence. But partition blocks should not be concerned with the structure of the red-black tree. It should be a responsibility of the caller. Because we call partition right before we're about to give the block to the user, right? The way we tell whether or not something is free is equivalent to saying whether or not something is in the red-black tree. So this is just saying, do this with something that is not in the red-black tree. Because if you do it with something that's inside the red-black tree, you mess up the entire structure. Since the sizes are going to change, everything is going to change. We considered including the logic of reinsertion into the red-black tree over here in partition block, so that partition block would be in charge of both things. That is a little bit of a threat for separation of concerns, but if it makes the code simpler, it would be better. The problem is that, once again, we call partition block right when we're about to give the block to the user, which means that if we perform a reinsertion inside of partition block, we're no longer going to know where the block that we previously had is. Because we're going to have, well, actually, no, we are going to know that, but we are going to have to remove it again from the red-black tree. I'm not sure if I'm explaining myself correctly. So I take the block from the red-black tree, I partition it. If the act of partitioning reinserts it into the red-black tree, I need to go back to the red-black tree and get it. And that is a little bit of a problem because red-black tree operation of deletion is log n. It is, if anything, the most expensive operation we can have. So not only are you doing that, but you're doing it 4 times or 3 times. The first time, which is completely unavoidable, but then when you partition and reinsert it, that reinsertion is log n. So that's 2 times of unnecessary operation. And then removing it immediately after, that's 2 more times. So that's 4 times of the most expensive operation in the memory allocator. So we're just not going to do that, right? We're just going to have to be clever and make sure that we do this with blocks that are not in the red black tree. So we first remove the block from the red black tree, and then we partition it. So have that in mind. Now, why do we need to partition the block? Well, we have the block's metadata. So the first thing we need to know is the block's total size, right? I need to know how many bytes are we playing with. So unit32t, sort of the total space, rather than size, the total space including what the metadata occupies. And that's going to be the block's size plus the size of a uint32t. So remember, a block size refers to this whole thing because of the optimization we just introduced. And now we just add the little meta field for size, right? So it's going to be the total space we have available. Now, they are providing us the size they need, right? So if I have this 52 wide block, to partition, right, this block into a 12 byte long one, and then whatever remains, I'm just going to pass 12. I'm going to tell it, well, I need a little block of size 12, and then you take a look at whatever happens with the rest. So the amount of size needed is 12. And we have established that the size needed is going to be in user size, right? By user size, we mean this thing, right? So it's going to be easier if we do it this way because of Malloc, right? Because now I just call, partition this block so that I can accommodate 12 bytes. And I don't have to worry about how big metadata is, how, whether it's allocated or free. You just give the amount that is needed. And so now the total size of the left block, total left space, it's going to be the size of a uint32t plus whatever the size they need, right? So that total left is whenever we partition, we're going to have this little 12 guy. 12, hello? 12, 12. We're going to have this 12 guy. And then this one is the one we refer to as the left block. Left. And this one on the right is going to be the right block, right? So the left block, the total space it occupies is whatever it provides to the user, plus the uint32 that's storing the size. And thus, the right is going to occupy, 32t. So total right space is equal to size of a uint32t. Well, actually, we would only need to say, well, the total amount of space minus the amount of space that's already being occupied by the left block. Perfect. Now, we need to assert that after these modifications, we're going to be able to store inside the block that's on our right the metadata necessary to establish what a block should be. So over here, it should be something like size of the block header plus the size of the block footer. So we impose the condition that if you're going to partition, you need for the block that remains, which would be this, to be at least be able to hold the metadata for a 0 size block, right? And that, because if not, it means that whatever remains just becomes like wasted space because we cannot keep track of it since it stops being a block. So we need to assert this. Not only that, but we also need to assert at the beginning that we're going to be able to accommodate for the usual metadata of this block. So how are we going to do that? What I mean is the following, right? Suppose, they call Malloc 12. Then size needed is going to be 12. So the total left space is going to be a uint32t, which is going to be 4 bytes, plus the 12, that's 16. But notice that 16 is not enough to hold all of the metadata that's needed for a block. size is 4, left is 4, right is 4, parent is 4. So that's 16. And then you need the footer information, which is 20. So we need this size needed to be at least 20. So I think we're just going to assert that size needed is at least 20. An alternative would be to grab the total left space and, have it be the max between this and 20. I nonetheless have a little bit of a problem with that, and it's the fact that the user requested for this block to be partitioned to like this specific size, and then we are under their back, behind their back, modifying the actual size that they passed to us. So I prefer that to be a user error, right? Like the user sees, oh, I'm using partition block wrong. I should have passed something that's at least 20 bytes long, rather than us secretly modifying the user's intention. The user being us, because we are the ones that are going to use this function. So now that we have those calculations, we know what the total left space is going to be. We know what the right space is going to be. What we're going to do is we're going to, let's see. So we need to include the metadata of this block. So actually, I think this is quite simple. So the left block now passes to be the block that was originally passed, right? Because this parameter, this block is a heap pointer. So it's pointing here. It previously was pointing to the huge block, but now after this modification that we want to perform, it's going to be pointing at the left block. So we can simply use block as the left block. And we're going to access that header. And what we want to do is set the size of that block, right? Now, notice that we cannot necessarily set the size with our member functions, which is the reason why partition block is a little bit more low level, because our functions, what they do, if we set the size in a normal circumstance, it's going to go, oh, that's a great thing. So we forgot about the footer. Great thing that we did this, because now we can just say size, and then this is equal to size. Perfect. So that's what I was going to point out, right? Set size not only sets the header size, but also sets the footer's size. And for that reason, we need to, because if we want to set the size of the left block currently doesn't exist. So it's going to look at the header, right? It's going to try and set the size, and then it's going to go to the footer, and then it's going to tell us that it's 12, which is actually not correct at all. But I want to make sure that we're thinking of things in the right way. It is very relevant because the size needed must be aligned. Great question. I think so, yeah. I think you're right. Yeah. It needs to be aligned since it needs to be aligned to at least 4 bytes. So it needs to be 4 byte aligned. Because the size information, this guy is going to be 4 bytes. So we need all of this to be also 4 byte aligned, so that everything in it, compounded is 8 byte aligned. Perfect. So, actually, I think what we need is something a little different. Not only that it's 4 byte aligned, but that its modulo 8 is 4. Right? I think that's a better way to put it. Yeah, because modulo 8 is 4, then you add the size metadata, and then it's actually 8 byte aligned. Okay, perfect. So I think there's a little bit of an issue, like, having this much of a requirement of something that what's supposed to be simple We need to fix this BS somehow. It's like this needs to be fixed somehow. Um, we will take a look at what the conditions are, like exactly, or maybe how we can make it simpler for the user. But for now, let's focus on the logic itself. So I'm gonna include the dessert. Now, there is something I want to put up to discussion. Maybe somebody wants to chip in. I'm not sure. But currently, our set size function, it makes sense that it modifies both header and footer. And I feel I would like to keep it that way. But there's also the problem that when we provide the the thing, wait, what about size needed? Yeah. So it is one of the alternatives, right? To align the size that's needed. I just that's why I said, like, fix this BS. I I'm not sure if if that is as straightforward, because if we align it, I mean, I guess we could, but now we are allocating a block that is a size different from the size that the user asked us to allocate. And so now it's like, I don't mean, the programmer asked us to allocate, right? So if I call this function, I pass it the number 13, I expect for it to partition the block so that the first one is 13 long and the second one is whatever's left. But if I receive instead maybe 16 long, then I'm going to be like, wait, what? What's going on? So it is a possibility. I don't think there would be any problem with that, to be completely honest. But I just want to think about it a little more deeply, because every decision we make is gonna, bite us later. So I just have this insert here, and like, let's focus on the logic itself. I think that is the solution we're gonna end up implementing, where we say, align the size that's needed. But yeah, that's the main thing. So currently, we need to, once we have that huge block, when we partition it, we access this header, and then we set the size, right? So if we take a look at how set size works, I think we would be completely fine. So, okay, extremely dangerous bug that we had over here. So, okay, this is where things start to get tricky. Footer, right? If you give me a block pointer, my only way of knowing where the footer is by reading the size in the header and then jumping by that amount and setting the size in the footer. Over here, we were introducing the most security vulnerability of them all, because we set the size on the header, and then when the footer tries to access the old footer, right? It was going to jump by that amount. No, actually, no. I think this is completely correct. Yeah, no, never mind. I'm just hallucinating. Never mind. Sorry, guys. Yeah, I think we're fine. So block header. Yeah. So I think what we want to do is simply, we want to set the size of a block to be, for this block, the left block now, we want to make it have the size needed. Assuming that size needed is exactly the amount we need and it's aligned and everything. And what that will do is it will grab this huge block, right? This huge block, and it's going to set its header to be 12. It's going to jump 12 bytes into the future and write 12 in the footer, right? But of course, since we're going to provide to the user this block, then this footer is going to be overwritten. I think that's something worth considering. Wait. So we only partition when we're going to provide the left block to the user. So that means that whenever is this something wrong? Yes, I think there is. Footer changes its behavior because of the new optimizations. So in the footer, as you can see, we read the size and then we jump by that amount to get to the footer. But remember that size refers to everything over here. So it refers to left, right, parent, color, the original user data field, and the footer. So now we need to subtract the footer size from here, right? Okay, it's getting really sneaky. Oh, so yeah, let's pay attention to that. I think it's like a very aggressive optimization, and that's why we're having those problems. But it's okay. So perfect. Okay, so we set the size of the block to the size that's needed, and now the footer is actually gonna go to the actual footer. So it's gonna travel the 12 bytes, and then it's gonna go back by 1, and it's gonna set this to 12. You may be saying, well, sure, but there's 2 blocks, so that's 8 bytes. And I'll tell you, yes, that's true. But remember that when we give this to the user, we're going to just delete whatever's in the footer, so it's completely fine. So we set the size to that, and now that we've set the size, I think we're completely fine, right? Because once we set the size, we have this field done and this field done. Since we told the caller that we don't worry about oh yeah, wait, you're right. The header also changed. So we need a pointer. Yeah, not only to that, yeah. You're right. So we just need a whoa. So to access the block footer, we just need the block size, and then we need to add to it the size of the header. Block header. Well, not the header, sorry. uint32 plus the block size, and then minus the footer, right? Which I guess you're right. If we just enter the block size, we're already offset by a uint32, and that's all we need to do, right? Yeah. So now we enter the lowest byte of the block of the heap, sorry. We change that to a constar, we add to the size, and that's it. Mem heap low, then we add the block location and then the size of the block. Yeah, okay, perfect. So we go to the lowest byte of the heap. We go to the offset that this heap pointer represents. So now we are at the head of the block. And then we skip by the amount of size that we have. Since the footer is only a uint32, then we would be totally fine. And then we get that. Perfect. Awesome. So now we can be over here and say, okay, set the size of the block to the size that's needed. So it's gonna go to the huge block, this 52 that we originally had, and it's going to set its metadata to something completely different. And through that, oh, sorry. Okay, let me delete this and this. Finally, okay. So if it is 52, right, then what this is going to do is it's going to set the metadata to be a block of size 12. So now it's going to delete this 52. It's going to put a 12 here, a 12, and then a 12 here. And that 52 is still in the footer, right? Nothing has changed about it. And so we have this, and I argue that the left block is finished, right? The left block is finished because we don't care about left, we don't care about right, we don't care about parent, we don't care about color, and user data is inherently there. So the only two things we needed to set were the sizes. Why don't we care about these? Because remember that we only do this with something that's not in the red black tree, so this information is bogus to us, right? So by just simply setting the size, we already position the block, which is perfect, right? So now we need to create the right block, which we do by simply setting the size of that block. And not only the block, but we skip the total space that's being used by the left block. That's going to be a heap pointer to the right block. So we start here, that's block, and then we skip by the total amount that the left block occupies. We skip over here at the beginning. Oh wait, I see a message in the chat. Let's see, what is... I remember I was building my alloc, realloc, and free with only mmap syscall. Custom implementation, by the way, in C, but feels like you do it in ASM. And I was allocating align size plus 8 bytes. First 8 bytes were for U64len. It was returning mem plus 8 because mem equals len. It was when I was trying to def custom C std. Damn, that's a pretty good challenge. Custom C standard library. But yeah, we have a sort of very similar approach to this. So instead of 8 bytes, we are working with we have the guarantee that the heap is going to be at most 2 to the 32 bits. So we are using size to represent, to be represented with 4 bytes instead. But it is the same, it is like a similar reasoning, right? Because the first 8 bytes were for U64len, yeah, it's similar to us. And it was returning mem plus 8 because mem was equal to the length. Yeah. I think these issues with alignment and everything, we're having the exact same situation here. I'm not sure if that's what you're referring to, but yeah, because size is 4 bytes, and then we need the actual thing that we're gonna provide to the user to be 8-byte aligned, or like the whole block to be 8-byte aligned. So the user section needs to be modulo 8 4, so that the 4 that are added from this guy make it 8-byte aligned in total. But yeah, I don't know. Or maybe you guys have a different suggestion of what it should be. But yeah, we're working with a size of 4 bytes in this case. We have, let's see, so we need to set also the size of the block. We skip the left block. And then we, after that, set the size to be, great question. So it should be the total right space that's left minus the amount of size that you need to store the size, right? So once we perform, we have the first left block. So what we do is we travel to the rightmost block, which would be here. And then we say, okay, how long is this block? Well, the amount of space that's still left which is all of this, minus the amount of space I need to store the size. So I think that's correct. And then once that's done, we have performed the partition, right? That's all we need to do to have a partition. And so what we return the right block, right? So because that's the block that just came into existence. The user knows about the left block because it's going to be the same pointer that they provided to us. And now we're just going to give them the pointer of the new block that came into existence, which is going to be block plus total space. Total left space. Also, I think this is the logic for partition. Perfect. So now we need to decide precisely the thing we were talking about. I think Penguin Operator was mentioning this, and same for Negvosa. Oh my god, wait, I didn't see all of the follows. Damn, the amount of people that follow. Thank you guys. Thank you very much for following. And yeah, dude, that's awesome. That's awesome. How much? We are at like 56 followers. You know, damn, incredible numbers. Incredible numbers. Anyways, but yeah. So what we need to do, right, is Nick Volsa, you're saying assert total right. Oh yeah, I'm so stupid. I'm so sorry. Yeah, total right space. Assert assert just some random number. Total right space. Yes, there you go. I think that's greater or equal to whatever this is. Um, Perfect. So now that we have this, I think we're gonna be completely fine. So we have partition. Give me 1 second, guys, because currently. Okay. God. So I have an internship, but I'm sacrificing my time to be here because I definitely like this a lot more. I'm just gonna work until late today. But yeah, so we have total right space. Then we set the size of the block to the size that's needed. We set the size of I think this is the correct logic. Uh, we have 37 minds looking at the code, so hopefully, if you find an issue, let me know. But now we need to go to this to-do. Now we need to fix this BS. What is this thing with assert, right? We need to determine many of the design choices related to how this function is going to work. So, size needed, right? It is better if we provide the user size that we need because as the programmer, we shouldn't be concerned with like the size of the headers and stuff because if that ever gets to change like it just did earlier today, we would need to change the entirety of the malloc code. So it's better if just we provide the partition block the size that we need for the user data, and once that size is provided, is it reasonable to align it to whatever we need, or do we require the programmer to do it? So the trade-offs here is the fact that we're creating a block of a size that's different from what the programmer specified. At the same time, the programmer is either way going to have to align that. So I think if it's either way going to happen, it would indeed be reasonable to align it to whatever we need it to be. Yeah. So, you know, I forget what the phrase for the wedding says. I think it was like, "Speak now or forever hold your peace." I think that was last stream we were talking about it. Um, for context, my native language is not English, so sometimes I forget some of the words. So I'll be asking you guys sometimes about it. But yeah, so speak now, hold your peace, because we're about to break a little bit of that autonomy that the user has. because we're gonna make the size needed be the following. It's gonna be if we align the whole block, right? Then we subtract whatever's here. Yeah, okay. So this way would be the way we could align it. So we first take a look at the entire block, right? The entire block is going to be 4-byte aligned. If it is modulo 8 equal to 4, then that means we need to add 4 more bytes. If it's already modulo 8 equal to 0, then we don't need to add anything, right? So if that is the case, if it's 4-byte aligned, if it's modulo 8 equal to 4, then this align is going to add 4 extra bytes. So the amount of space that we're going to give to the user is going to be those plus 4 bytes that come with the align minus the size, right? So we're sort of like, we have the block here, right? And we are the world. We are the children. We are the ones who make a brighter day. What was it doing? Yeah. So we're taking a look at this block, right? And then all of this is going to be the user thing that we're going to provide to them. And so what we do is we say size, and then this block. If aligning the block involves adding 4 bytes, 1, 2, 3, and 4, then what we do is after this alignment, we say that the user section is going to be all of this minus whatever we use for the size, right? And so now it's going to be all of this, which is exactly what we want. If it is modulo 8 equal to 0, then we don't add anything. And so user size is going to be the entire block minus the size. So it's going to be this. So either way it works. So I think we can just do that, right? Perfect. Awesome. I think, yeah. I think we're in the right space. We can definitely make this be here before the 20. Yeah. Okay. Perfect. Everybody held their peace, so hopefully we are we are peaceful right now. We are, satisfied with the partition block function. Something that I think we've been lacking is testing as we develop. We already tested the red black trees, so like at least in the previous implementation, so I think we're fine with that. But I do want to start, being involved in the habit of oh wait, Satrack75, thank you for following. Yay. I think okay, we got a lot of followers today. This is absolutely awesome. Notebookik, Viado6, Gatman 619, Hanso High, Night Like 90, Panda Punk, JBJ War, Happily Lost Child, Euros Gaia, not sure how to say it, Void Reasoning, Lolero Empastillao, and then in Ion and Satrack75. Thank you guys for following. And yeah, hope you're enjoying the stream. So people, we need to log in. We need to focus. What were we doing? I'm gonna suffer from Alzheimer when I'm old. Anyways, partition block is free. Yes, we were looking. Oh yeah. We need to test as we develop because this is such a fragile thing. Like we're working at a pretty low level to the point that like, a single bit being 1 or 0 matters a lot. So it is ideal if we can work on tests while we develop. So I want to test this partition function. So let's simply create something like test partition block, partition block. right? And what we're going to do is we already initialize memory here. So we can, well, I guess we need Malloc to already be implemented, right? Yeah, I think we're only going to be able to test this when we implement Malloc. Right? Yeah, because it depends on like set size, it depends on block is free. So, okay, does anybody have an idea of how we could test this without having written Malloc? Maybe we can just copy and paste this code over here and then just like do whatever we want. I'm not sure. Because that would also imply changing the functions and all of that. So okay, I think I'm gonna do something similar. So memlib here, I think I wanna be able to pass to meminit not a void parameter, but instead pass to it some sort of char pointer that's gonna serve as the heap. If it is null pointer, then we do whatever we've been doing already. So maybe we pass a char pointer, which is the heap, so that we can take control of the heap and know where it is. And now on the here, we can simply say that the memory slot break is either going to be if heap is not null, then heap. Otherwise, make it be the malloc for max heap, right? So this way, we can now say, you know, well, yeah, I suppose that if we have this, yeah, heap in C, right? I'm not sure if in C. So if I do this, is it allowed, or do I need to do the, heap is different from null, or does C just immediately take note of that? I think it does. I think we would have no problem, but let me know. F we exit with 1, and then we make the max address be this. Perfect. Okay, so once we have the heap be that, we have control over what the heap is. So I think we can just say just heap, and that's going to be like a malloc of, I don't know. Let's just use 128. And of course, we're going to need hashtag include std. Oh, I forget what malloc is declared. Do you guys remember the header? Is it not stdlib.h? I think it is. Yes, okay. Perfect. So meminit, and we need initialize memory by passing in this heap. And we should also be able to pass in the size of the original heap. So OG size. And by that I mean heap is empty initially. No, I do not want that. I want it to be the size that they pass me, the OG size, right? An OG size could by default just be 0. And then we just need to update the signature. So heap OG size for uint 30pt. Perfect. So I think that takes care of everything. Oh, does C not have default parameters? Wait. Wait. Okay, my PC is going to lag when I open Firefox, so beware. Okay, I think we're back. Okay, C has no default. Oh, okay, that's sad. So I think we can just simply let it be, and yeah, and then just pass 0 all the time. So whenever we initialize memory, we want the heap to be this, and then it should just be like the usual 128 bytes. Perfect. Awesome. So now that we have this, it's going to be easier to play with. I actually think I want the heap to be accessible from everywhere. So let me add the static variable, char heap. There you go. So now, perfect. All right. So now that we're here, let's see. When we want to test a partition for a block, we initialize the memory, we do all of that, and I just want to delete this because instead, what we're going to do is we're going to call test partition block. Right. Perfect. So to test the partition of a block, we can simply create the heap ourselves. So what I'm going to do is introduce a block at the beginning. So we do something like, block set size to be 124 bytes. Is that right? I think so. So the block at heap pointer 0, and I want it to be 124 bytes long because the size takes 4 bytes and then, right? So it's going to be the initial block. Then this huge block, we want to partition into 2 blocks. So now what we want to do is we want to call partition block. Wait, is that not a thing? Partition block, yeah, it should be fine. So whoa, what's going on? Okay, partition. Hello. Oh, I think it's not declared in the header. Okay, I'm just gonna add it here as temporary, temp, because we don't want that function to be public. But let me just, just for the sake of the testing, partition block, and partition block is gonna accept a key pointer to the block you want to partition, and then the size of the left guy that you want to obtain, size meter. Perfect. So that should be it, I think, question mark. Is that the right call? Yes. Okay. So now we're gonna do partition block. Let's wait for it to, error while processing. Unknown type, uint32. I meant uint32. uint32. Perfect. Okay, so now we can do partition block. Yes. So you want to partition the block at heap pointer 0. And let's partition it into, I don't know, right? I say I need 12 bytes, right? Perfect. And then we can sort of inspect our memory, I suppose. So there are 2 approaches we can have. We could have something that just prints the state of the heap, like little blocks and stuff. Or we could just go inside the memory, the memory inspector, and just take a look at what memory looks like. Does anyone have a preference for it? So what I mean by that, it's like, the memory inspector just allows us to take a look at the memory, but it allows us to look at each by memory. Do you prefer the memory inspector, Fabiak? Or do you want us to print? Well, I guess a test should be something that I prefer what you prefer. Oh, thank you. Thank you. So one thing here to note is that a test should be something that, whenever we run the test, we know whether it's correct or not. Cliff Bites, let's do it. Oh, welcome to the chat, Cliff Bites. Let's see here. Yeah, wait, what? Why do you have a little crown? What does the crown mean? Oh, damn. It's a Prime user. Damn. Pretty good. So, yeah, let's do both. Could be. So what I'm thinking of right now is the following, right? Whenever we implement a test, ideally, we want the test to tell us whether things are right or wrong, right? Because right now the way we are directing it is like we run it and then through the debugger we inspect memory to see if it's right or wrong. I would want to have something that is automatic because that is supposed to be the purpose of a test, I assume, right? Maybe. So maybe we can develop like you know, helper functions to be like, check the integrity of a block and check that this thing is actually happening. Um, hmm. So how could we do that? Do you understand the things that you've been seeing? Let's see, check block. Check block. I think we can develop a function called check block that simply takes a key pointer to that block and we ask the information that we want to know about it. Maybe. Right? Does that I feel that sounds reasonable. Although most of our stuff is going to be related to like, is this in the correct byte? Is this not in the correct byte? Okay, for now, for now, let's do the memory inspector, right? So that we at least know that like things are going the way they're supposed to. And after that, we sort of start worrying more about automatic tests. Non-void function does not return value. Oh yeah, yeah. So we just simply return true, as in like, yes, we passed. Um, yeah. So let's think about it. I think we're completely fine. So let's do GCC. What do we want? We want mmtest.c. We want to include also memlib.c. We want mm.c. And then finally, we want the red black tree.c. All of that are going to be outputted to mmtest, which we have from last session. Okay. Non-void function does not return a value. Where is this? Line 136. Oh, petition if worthy. Okay, I think we're just gonna comment this one out for in the meantime. And line 150. Line 150. What are you? Oh, Malloc. Okay, no, we just returned here. Yeah, I think we're hopefully fine. And ooh, litter ally or L1 ter 4 lie. Welcome and thank you for following. Yay. Okay, perfect. So notice that over here, what we have is, I think, everything. We have everything needed for success. Okay. So let me reset this. Hopefully we can compile this. Yes, perfect. And now if we run the debugger, hopefully we can stop here and here and here. Let's go. Run the debugger. Immediately seg faults. Let's wait. Let's see what happens. Hello? Paused on step. What do you mean you paused on step? Paused an exception? What? Nothing has happened. Well, what? What was the exception? What? Huh? Am I? Oh, this is the same thing as last time. Sorry, we forgot the debugging symbols. Yeah, dash G, dash G. Okay, perfect. Yeah. Okay, I was getting worried. Let's go. Let's wait. Hello to all the 36 viewers. This is absolutely insane. Our previous peak was like 18, I think. And before that, it was 9. Our current peak is now 55, if I remember correctly. So, yeah, very interesting. Thank you. Welcome, everyone. We're now trying to test one of the functions for the memory allocator. So we are here in main, right? We allocate the heap, now we initialize memory, and now we come here. So we set the size. So this is interesting. This is something we should see in the memory inspector. So currently, oh, brother, where is the, anyways, where is heap right now? So what is the address of heap? So the address of heap is this. That's going to be the beginning of our heap. So we want to travel there. 0x 1 2 3 4 5 6 7 1 1 2 3 4 8 1 2 3. And then we want to take a look at 4 megabytes of data. Perfect. So this is what a heap looks like. Completely weird information. So if we set the size of the 0 block, we should see this guy changing to be 124, and then the guy at the end of the heap to also be 124. Well, what happened? Wait, does memheap point to these locations? It should. Oh shoot, the variable became invisible. Hello? Oh, okay. Oh, memheap is pointing somewhere completely different. What? Why? Why? Memlib, memlib_c. So memheap should be pointing at the lowest byte in the heap, which is memory start breakpoint. And we set memory start breakpoint to be, yeah, to be the heap, right? Am I missing something? Or does it just not? Yeah, no. I think we're fine. We should be. Can I see what memory start breakpoint is? I don't think we are inside that phone. Oh, where it actually. I think. Okay. This goes back to the question of whether or not I could do that. I think if I just do this, we should be fine. Let me just recompile. So reset, and then recompile again. Recompile. La llamada del tiempo. J'ai besoin de memoria. Okay. Let's run it. Let's see. Will it work? Place your bets. My bet is yes, it will. Hopefully. Perfect. Okay. We allocate the heap. Everything is at 0. After a minute, these guys should obey our orders and become whatever that number is. Well, why? So it's currently not. If heap is different from null, okay, I'm gonna introduce a breakpoint here. I don't know what's going on. Maybe this is just my inexperience with C, because C++ would do this, right? This would be valid in C++. Let's see. So, sorry if my PC is a little slow. It's not, streaming consumes a lot of the CPU and the same for memory. So sometimes it's a little slow, but patience with her. Is doing her best. So heap. Whoa. So it is actually doing what we're asking it to do, no? Because if memheap and memstop_bok get set to that value, yeah, so it's actually being set to what it's supposed to be, right? It's actually cam is lagging sometimes, but no problem at all. Oh yeah. So sometimes when I start a new program or something like that, it she started struggling a little, and then then it stabilizes. So yeah. Perfect. So let's see. If we have the memory start breakpoint here. And the heap pointer, according to mem_init, is this. Oh, I'm stupid. I'm stupid. Oh my god, guys, am I stupid? Yeah, I'm taking the address of a pointer, which is not. Okay, dude, that was such a rookie mistake. What is going on with me today? Yeah. Okay, now it makes sense. Now it makes sense. Now if we proceed, we get here. So we continue to the next one. By the way, I want to remove that breakpoint. Okay, I was all over the place. We test the petition, yes. So now we need to go to memory inspector. Yeah, now it's worth it. And we add a new memory view to go to whatever that is. 0x123.123.1005F5AC0, which should be the beginning of our heap, and we want to see 4 megabytes into the future. Perfect. So everything is zero now. If things work, people, we should see this byte being changed to a 124, which I'm not sure what it is in hex because yeah, I will need to. Let's see. Yo, let's go. Let's go. Wait. Okay, stream is about to lag. Sorry. Wait. Um, guys, did I lose you for a second? I think I did. If I open Firefox, it's gonna be words now. Yeah, wait. Um, okay, I think we're fine. Are we back? Yeah, I think we're back. Um, hex to decimal. I want a converter. So just beware that if you see me opening a new program or something like that, there's gonna be like a little bit of lag. It's not your problem, it's my problem, but it stabilizes eventually, right? So, oh, Mac OS calculator has a built-in hex mode. Open calculator and press Command 3. Oh, what? Really? Wait, calculator. I've also never used the Mac OS calculator, so maybe I should now. Um, let's wait. There you go. Okay, and you're saying Command 3? Let's see, Command 3. Oh, damn. Wait, this is absolutely perfect. Wait. Might have just saved the day. H. Go Schwetz. I'm not sure if it's Hugo Schwetz, maybe. No. Let me know how to pronounce your name. 'Cause I wanna get it right. But yeah, okay. So 7C, if I remember. Let's see. Hello. No. Oh no, we did. Okay, that's actually on the slide. And now what is this? So yay, Flux Sticker. Thank you. Yo, this one's some RAM or a new CPU. It's this laptop I have, it was gifted to me by the parents of my girlfriend. I'm very happy with it, and currently I'm like traveling. I'm like in an internship in another city. Back in college, I have the PC that I had for like 7 years, and that was a little bit better. It's like an actual tower. So yeah, just wait. If you wait like uh 2 more weeks from now, or 3 weeks, between 2 3 weeks, we got better streams hopefully, because then I'll be able to use the computer I usually use. Now we're using it through a laptop, but yeah, gonna be the best stream ever. Anyways, we particularly okay, all right. We need to focus, people. We need to focus. Pay attention. Um, when we partition the block, we want to see the change to 12. So this should be 12. And not only that, but how do we have? Okay, we have 16 byte process, which means that this byte over here should also be 12. This one. And then this one on the side should become whatever the remaining space is. So 128, right, minus the amount occupied is 16. So that would be 102, if I remember correctly. No. 112, right? 112. 112. And so 112 left on the side should be 108. So we should see inside of here 108. Here we should see 12. Here we should see 108. Correct me if I'm wrong with the arithmetic because, often I make that. So step over, prepare, 3, 2, 1. Oh no! Wait. Um. Oh yeah, this is the thing that we set for the metadata, or something. Um. Yeah. So I think. Okay. Let's be a little 12. Let's you know. I feel like okay now I realize how annoying this is. Like I feel you guys may have been right, especially Nick Vosa, I think was pushing for this to be the case. Where instead of the assert, we just do the match between that and 20. Um, I'm not sure though. Let's simply just make the test accumulative 24, and so that way we can let's reset this, and then we have this. Add a bit of delay to your stream. It will normally fix the lagging. Oh wait, is it lagging right now? Oh, I think it's lagging. No. Wait. Sorry guys, wait, give me a second. I think if I close the calculator and as everything, the problem is the browser. So if I just close Firefox, hopefully there will be no more lag. Hopefully I recovered you guys just now. Yeah, I think, yeah, when I open Firefox, things go south. So, are we stable now? I think so. I'll go to the VS Code and see if it drops or something. So we're at 6,000 kbps, 17,000. Ooh, it's become volatile again. A few days ago, we had some problems with the stream where it was like going up and down, up and down, up and down. Um, yeah, thank you, Nick Vosa. Yeah. I think $5 was the issue because now I'm getting like good thingy guy or yeah. I think I'm getting 6,000 something. Ooh, it's going. Oh no, wait. Um, wait. Guys, can you see me? Is it lagging a lot? Cam freeze? Oh no, wait, no. Okay, what happens if I do this? Is it back? Hello. The whole stream is freeze. Wait, no, no, no. Wait, uh, I suppose some of you can hear me? Okay. The root of all evil was Firefox. We opened Firefox and everything failed. Nice PowerPoint presentation. All right, buddy. You're the verge of banning. Okay, so let's see. Hmm. Yeah, we may be having some trouble. Okay, what happens if I change to this new scene? Like, do things start to change? Like, can you see my face and everything? Try maybe without the face cam. Yeah. Okay. Let's see. If I hide the face cam, there. I hit it. There's nothing now. Oh, it's stabilized. Oh, the problem is the camera. What? Okay, that's kind of crazy. Why? Huh. Okay, and then hopefully everyone can see the stream normally now. I see the kbps and it's currently there. So okay, real port buster. Is this memory allocator on GitHub? Yes, yes, we have it on GitHub. Um, the GitHub is, I would show you, but the problem is we cannot open Firefox because then all things go bad. I think the link is https github.com slash, my GitHub is slash SharifSegfaults. So it probably would be something like SharifSegfaults slash Malloc, if I remember correctly. That's gonna be the thing. But yeah, I wonder. Okay, let me see. Is the camera the issue? If I enable the camera again, will we go black again? Um, hello, this is me again. Oh, we're still stable. Wait, what was the problem then? Um, bro, what? Okay, yeah. Yeah. So that is the way things are. Unfortunately, sometimes OBS just likes to throw a tantrum. I've discovered something. Um, to those of you that were in the stream where I couldn't get OBS working, I remember Nick Vorsa was there. I think Andrew was also there. Um, I couldn't get OBS to work because it would go like up and down in the kbps. I discovered that if I set the resolution to 12 to 720p, save, and then immediately change it back to what it originally was, it fixes the problem. Like I don't even decrease the resolution. I like trick OBS until like, oh, let's decrease the resolution, and then after that, I set it back to what it was, and then it just immediately fixes itself. So it's very interesting, you know. Maybe some not freed up memory. They need your code. Yeah, yeah, it's probably something like that. I'm not sure. Firefox definitely. I mean, all browsers in general, and I'm not sure. Maybe the camera software, like something. No, no. Wait. I was seeing the kbps and it's going down again. Oh wait, no, we're fine. We're fine. It's just that I clicked on VS Code, and when I click on VS Code, it like. Anyways. Guys, give me 1 second. 1 second. I mean, 2 minutes. 2 minutes. I'll be back. I'll be back. Uh, let's see. Okay. Let me read the chat for a second. So yes, I see it. Are you a C beginner by chance? I am a C beginner. Yes, this is the first project serious project that I do in C. I mostly code in C++. So like I'm, C is pretty familiar precisely because of that. It's just that I'm so used to C++ that there are like things that I tried to do, and then I realize somebody tells me like, oh, that's actually not in C, and then I'm like, oh, okay. Well, um, clarify tests. Use Vim. All right. Okay, buddy. But yeah, no, I feel it genuinely, like and I think I mentioned this in a previous session we had in a previous stream that I want to start using NeoVim. It seems like a good editor and everything, and like, you become like a wizard with a keyboard and whatnot. The problem, tiny little problem. I don't know how to type. I don't know how to type on a keyboard. Um, and by that I mean I still need to look at the keyboard to type. So I learned like all of programming when I was like little, and so I never learned how to properly type. So I just like developed my own way of typing, which is still involves looking at the keyboard for like a split second. So I feel like a bottleneck in my editing is my typing itself. Once I fix that, we can start using maybe NeoVim or something like that. Um, Too much delay. Okay. Guys, relax. So I think something we can do. Okay, when I say, I'm gonna say three, two, one, go. When I say go, type one in the chat, just so that I know what the delay is. Okay, so let's see. Three, two, one, go. One. Oh, brother, we have 2 seconds of delay. Why are you guys not gonna? Okay. If you add a bit of delay to your stream, it gives more time to Twitch server to process and reconcile the video feed, which helps prevent buffering and lag on our end. Oh, that'd be great. I think I okay. Let me write that down in my to-do list, because I think that if I do it right now, like I would need to end the stream and all of that. I like it when the VODs are like, all together. But that is a great suggestion. I'll look into it. Let me write down here in my to-do list. So, um, add a delay to stream for Twitch to reconcile video for viewers. Perfect. Yo, okay. That's a great suggestion. Um, Gawaringo. Your first time in chat was the number one. That's great. Oh, Net Vorsa, you're behind by a lot. Um, yeah. Cool. Yeah. Andrew, I don't really think NeoVim solves typing speed. It's more about making types of edits. Yeah. Exactly. Like NeoVim doesn't solve the typing speed. Like it's our problem. I like typing speed is a prereq to NeoVim if you really want to like be efficient with it, I suppose. Because of like, if it's difficult for me to think about which keys I want to press, it's gonna be difficult for me to think like, D for the lead, P for paragraph, A for next word. Like it's so yeah. Nick Volsa, yeah, I think you should just refresh the stream and then come back. And then probably you'll be on with the rest. Because everyone was like 2 seconds behind. But yeah. Lesson of today, never open Firefox. Can you imagine how it would be with Chrome? I feel like if I were to use Chrome, it would be catastrophic. Helix for 2 years when mathematics is close to Yules. Oh, interesting. So maybe I should just try it out. I don't know. Wait, actually, that's a good motivation. But yeah, let's see. Okay, we came back, and what we were doing, we were working on the memory allocator. Oh yeah, we were inspecting the memory and all of that. Okay, so we grab the heap, we initialize the memory, we test partition. There you go. Okay, now we go to memory. It's gonna be a different address now. And so we had a memory view for 0x000. So 3410005B1 B00. And then we want to look 4 MB into the future. Perfect. So now when we set the size, we should be able to see the 7C that we saw before. Perfect. Awesome. And now we should be able to see Sorry, these things are running out of battery, and they're the only microphone I have. Um, so let me charge one of them while the other one is. Wait, let me see. Which one has the less battery? Oh, the right one has 10%. So let me use the left one, and then I can put the right one in. I think we're still good. Yeah. Okay, we're still live. We are still live. So when we partition the block, 24 should be around. Let's see. So this thing should change to 24, and then 1, 2, 3, 4, 5, 6. Here we should see another 24. And after we see that 24, we should start seeing whatever the remaining thing is. So it would be 128 total space minus whatever the left occupies, which is 6 plus 7 bytes. Yeah, 7 bytes. So 128 minus 7, 121 minus the one from the size, 120. Right? 120, I think. So we should see a 120 here. So remember, put this in your mind. 120 over here, 24, and then 24 somewhere around here. Here. 24, 24, 120. Andrew asks, why are you streaming so early? Oh, Andrew. Because we need to fix our sleep schedules. We need to fix our sleep schedules. Since I was streaming like in the night or like 6:30 where I am, I would go to bed at like 2 a.m. or like 1 a.m., which is really bad. And also for the people in the US, it would be really late. It would be like 7 p.m. For the ones in the east coast of the US, it would be like 10 p.m., 11 p.m. And for you guys in Europe, it would be like 4 a.m. or 3 a.m. Like some weird schedule. So I think this new schedule is a little bit better, because now everyone gets to sort of watch the streams in a more comfortable way, and also for myself too. It's a motivation to wake up early and get a routine and so on. And some of you guys, I think the majority may be at work, so you can just have me there in the background making noise. Like, I don't know, but more people are awake, which is great. And yeah, so my commute from work. Yeah, perfect. Yeah, exactly. So now I think you guys' day has finished, right? Because it should be like what? Currently it's 10. So it's probably like 8 p.m., 7 p.m. And thus I think you guys are just coming back from work, which is great. But yeah. Everybody get ready. Get ready for this epic moment. If it works, we have effectively tested it. Um, what? um, Hello? Oh, wait. I think we succeeded, no? Did we? Did we? um, yeah. Each of these is not one. Okay, because in the drawings, I make every block be 4 bytes. So I was like, oh, it should be over here. But no, that's not the case. Yeah, it should be like, these are actual bytes. So let's see. This should be equivalent to 24. I mean, I guess we can just do the mental calculation. So A is 10, 13. And then one on that side, that's 23 now. Okay, I don't want to open Firefox to look it up. I'll look it up on my phone. Uh, just to make sure, because if not, then the stream collapses. Twin 1C hex to decimal. 28. What? Yeah. Why are we getting 1C? unsolved mysteries of the current world. Why are we getting 28? Um. Oh, I know why. I know why. It's because so we specified 24 for the user data. So the four that are added for the size are what make it like, 28, right? But it needs to be 8-byte aligned. And so it adds 4 bytes to the user section. So now it's 28. So I guess it's correct. Yeah. So 1C, yeah. And then in the 27th bit of the user section, we should see so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Yo, let's go. Okay, that's awesome. Now, hear me out. What's going on? Okay, why is this 5C over here and not over here? Do we have a problem with alignment? Because it should be 8-byte aligned, right? Every block is 8-byte aligned. So why are you here? This doesn't seem right. Oh no, I think it totally is. Right? Yeah, I think it totally is. Sorry, the NDNS is confusing me. 1, 2, 3, and 4. So this is the U in size 32. This is the size, right? Yeah, I think it's the NDNS. Yeah. So these 4 bytes represent the size. Yeah. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. And then we have the actual, the last 4 bytes completing 28 to what the user would effectively see. Absolute cinema. Absolute cinema. Perfect. So that means that the next block should be, I said 108, right? Something like that. Let's see, because this whole section is 32 bytes. So 128 minus the 32 should be what, like 108? You add the 2, no, 98 or something. 128 minus the 32, 96. Yeah, sorry. Whoa, I don't know what's happening with my mental math. 96 bytes left for the other block. And then 96 minus the initial 4 bytes of the size should be 92 bytes. Is 5C 92? Great question. Let's look it up. Hexadecimal, and then I'm going to put 5C. Convert. 92. 92. Let's go. Yay. Okay, that's perfect. And I will just assume that, this guy's in the correct position. So it seems like our thing is working. Partition block is working. We can be relatively sure of that. How sure? We don't know, but kind of sure. There is some notion of sure we can be. So, yeah. So assert we have the size needed, schedule equal to 20. I think partition block is fine. We're just gonna assume it's correct. Okay, I understand. Listen. So I know. We need to introduce automatic tests that detect whether or not the function is correct. Yes, I know. It's just that right now it's maybe a little bit more a little bit tedious. I just don't want you guys to spend the stream looking at me being like, all right, let's now inspect the 28th byte. Like uh trying to create the automatic test. So let's just leave it at that. Partition block, we have it, right? End of discussion. Okay. Now there is this function called partition of worth it. Now you may be asking, what is partition of worth it? Partition of worth it is whenever we encounter the dilemma of partitioning a block, and I'm sure, you know, especially Nick Vos is going to be they're like, brother, you've already talked about this like 20 times. I know, but there's more people in the stream, so you are going to also listen to the explanation. I'm sorry. So whenever we have a big block, right? Right? Suppose this block is 52 bytes wide or something like that, right? So 52. Let me increase the size. 52. 52. There you go. 52. Let me, yeah, sort of expand this a little more. There you go. So it's 52 wide. And suppose the user asks us for 48 bytes, right? Then we're going to provide to the user all of the first 48 bytes, and then we're going to be left with like 4 bytes or something like that. Now, the question is it worth it to keep track of this tiny little block? Because remember, this is a tiny block, right? Nobody is going to ask us for like, you know, Malloc 2, right? Like, you know, that would be insane. And either way, we can just serve that request with basically any other block in existence. So storing blocks that are like this small actually hurts our performance because if we are to keep track of them, they need to live inside the red black tree. And if they're living in the red black tree, it's more nodes inside that red black tree, which means that now our search term is going to be sort of impacted by this. So instead, what we can do is, rather than providing to the user 48, we just provide the whole block so as to not worry about this little guy, right? So that's exactly what this function does. It's like, is it worth it to partition the current block? Or should you just use the entire block? The rule of thumb that we ended up determining last stream in a little bit of a discussion was this one over here, which is written in the code here, right? We first look at how much space is occupied by the block, by the huge block, and then we say, after allocating the left block, how much is left? If there's at least 64 bytes left, then we should be fine, right? So it's just like an arbitrary, you know, arbitrary metric. I just implement it as a function in case we want to change that heuristic. So the amount of block space that's being occupied is going to be the size of a uint32 plus the size of whatever this block is. So that's the total amount of space that we're using. And with this total amount of space, we subtract from it. So if from the block space, right, we subtract the amount that would be needed. So left block size, space actually, space, would be the size of, I think we can just, you know, it would be exactly just this. So size needed would just be this guy, size needed, and then total left space is still total left space. Yeah. So size needed, and then here, instead of space needed, it should be size needed. And I think that's fine. Yeah, okay, so the total left space is going to be that, and then we subtract from it the total left space. If there is at least however many bytes we want left, so I'm just going to mark that with an X, then we're going to partition the block. Then we return partition the block, partition block into whatever the size that's needed. Otherwise, we simply say, well, no, we return a null heap pointer, right? And so that way, we can have a heuristic for that case. Now, given that the amount of, so the previous 64 bytes accounted for the metadata, right? But remember, the metadata has been reduced by an astronomical amount. So now we only have 8 bytes at the start, right? And so what we're going to do is, instead of 64 bytes, maybe we want, okay, what was the rule that we determined? I think it was like, if the remaining block is allowed or it can host a relatively decent sized allocation, then we're good to go. I think a relatively, a decent sized allocation maybe is 16 bytes, right? So then plus the 4 that you're gonna need for the for the for the for the size. There you go. It would be 20. Let me check my battery. Ooh, 9%. Okay, that's dangerous territory. Let me. Andrew Krevsky. Oh, it seems like you guys know each other. Penguin operator saying hello. You should return the block itself. So currently, the way it works, it's like whenever we partition, right? What we return is the block that just came into existence. So the left block, the user has access to through the pointer they gave us. They don't have access to the block that just came into existence, which would be the right block. So we always return the right block so that the user knows, like, oh, okay, right, this guy. So here I'm saying, if there is a way to partition, then I just return whatever partition block returns. If not, then I just tell it there was no right block. And so now they're gonna know, oh, it's the entire block. Because they already have access to what this block is. So that's like the standard we established. Yeah, I think if it is greater or equal to 20, it would be able to host a 16 byte allocation, which I feel is very decent, right? See, 16 bytes, pretty decent. Not too crazy though, but still decent enough. So yeah, okay, partition worth it. I genuinely think 16 is still a little small. We'll see. Okay. So that's partition worth it. And I think actually, I also want to get into the habit of committing more often. Because I feel we've been committing like we only have like I think we only have like 3 commits in the entirety of the. Oh, never mind. We have a first commit, the initial scaffolding, then we added a red black tree, then the initial Malloc implementation, and then I removed the test scaffolding. Okay, perfect. So yeah, we've basically done only 3 like actual commits. So let's commit more often. Get at dot. I know. In this channel, we do get at dot because it's a relatively small folder. It's oh, never mind. Get ignore. We need to ignore the debugging symbols or whatever. Ignore any sort of folder that starts with vsim. I think that should be enough. Slash. And do we need to ignore anything else? I think we determined that the Excalibur was being pushed. So let's do that. I just want to delete this guy. Move to trash. Yeah. And git add dot. And I think with that said, we're able to commit? Question mark? So let's commit. And here, feet, sort of add partition block. Or I feel it's better if we simply create a branch. from here, git checkout b, and let's just call it, what should we call it? Refactor slash malloc rewrite. That's a very sensible name. Pretty good. And we add everything. We add everything. Hello. And then we commit that with refactor, and then implement partition block and partition if worth it. I think that was the, yep, partition if worth it. All right, people. I think we have it. Awesome. So now we're gonna git push. Want to set it upstream because I don't have this branch in the origin, and I think that's okay. Refactor slash malloc rewrite. Awesome! Yay! Let's go. So you should be able to enter the GitHub. Okay, I don't want to open Firefox right now, as we said. So https github.com/SharifSegfaults. That's my profile. So it is public repository, so you should be able to see it there. And I think that if you add /nalloc, you'll be able to see it. So yeah, all right, perfect. So let's see. Here we have the block space, one of the total space. Yeah, 16 bytes of allocation. I think if the remaining block can host a 16-byte allocation, let it live. Let it live, let it live. Okay. Perfect. Partition worth it. Yeah, I think we're fine. Great. So now, Infinite Coder 01 is rating. Whoa. Thank you so much. Thank you so much. Yay. Dude, awesome. We've been rated like twice today. That's absolutely incredible. Yeah. Automode stopped my raid message. No, don't worry. I allowed it. There you go. Yo, hello, Infinite Coder. Yeah, we're working on a memory allocator in C right now, and yeah, welcome guys to the stream. We've been working on this function called partition block, which allows us to partition a memory block into a smaller set of two memory blocks, and that's the way blocks come into existence in a memory allocator. And this guy, which only performs a partition if it's worth it, right? So Nigel with throw. I use Helix too. Guys, what is wait. What is Helix? What is Helix? I'm so intrigued. Should I risk it in Open Firefox? Yeah, I'm gonna look at it on my phone because when when I open Firefox things go bad. What's the Helix? Helix IDE. I imagine it's an IDE. Oh, this looks pretty. Interesting. What is it written in? Vim-like modal editing. A Cocoon NeoVim Smart Editor written in Rust. Oh, pretty good. Excellent. Oh, interesting. You guys are. Where are you from, by the way? Oh, I am. I am from Colombia, South America. So my original language is not English; it's actually Spanish. And if you're asking about the accent, I learned English by myself when I was a kid, and since I was a kid, I used to watch a lot of British YouTubers, and slowly but surely, I picked up on their accent. So I am the compilation of all those British YouTubers. So yeah. Colombia. Yeah, Colombia, but with the O. The country in South America, not the like city or things like that. But yeah. So we were building a transpiler from Rust to C. Brother, what? That's absolutely incredible. See, this is like, I'm not, it's one of the things that puzzles me is like all of you are like experienced coders and everything, and then just decide to join this like random guy stream, coding a memory allocator, and then I'm like asking questions to you guys all the time. I guess it's a very good community. I felt very welcome. But you're Russian, by the way. Yo, excellent. Russia should be like 10 hours offset from now. It's probably like 8 p.m. maybe. I think 8 p.m. 8:37 p.m. You're coding Elon Musk from scratch. Okay, gonna make us all millionaires. Don't forget about us, agentic life. Anyway, um, I see. All right, Infinite Connor. Russia has like told. Oh yeah. You're right. Yeah, if you're closer to the Eastern Europe side rather than the Asian side, then okay, yeah. I suppose. So probably it's like between 8 and 10 p.m. 8 p.m. where you are. Okay, yeah, it's close to West Russia. Okay, Russia. Okay, well, let's see. Okay, let's continue with the memory alligator, guys. Don't rally the truth. No. Let's see. Okay, we have focus, lock in. Partition block and partition aborted. We just started the these functions. We finished with them. Now we have the pleasure to be writing Malloc now. So perfect. Now with Malloc, what we're going to do is a couple of things. So this is you think this is easy. You would think this is easy, but it's a little bit complicated. At least for me. I'm not sure if I've been able to wrap my head around it completely. But here we have the code we had previously written for Malloc. I think we need to revise it for sure. So one thing that I think makes a lot of sense and I think was not wrong is the initial lazy allocation. So if a user is using if our user is using our malloc, right, then sure we can support all the data structures we need. Let's see. Ich spreche Spanish nicht. Ich kenne Russisch. I was wondering again, by the way, English, Deutsch, and Niederländisch. Okay, interesting. So, don't speak Spanish. Okay, I see. Russian, Korean, and English, Deutsch, and damn, I have a lot of them. Pretty good. So, yeah. Oh, um, I'm scratching my body. Okay, what are we doing? Yeah, many languages. Um, all right. So we have our malloc here, and what were we doing? Oh yeah. We were doing the following. So when we so we could have two types of users. The users that use malloc, for which we need to insert our data structures and stuff. But if a user doesn't want to use malloc, then if we perform sort of the initialization of all the data structures inside of init, we would have a problem, right? Because that user doesn't want to use malloc, yet the malloc data structures are taking some sort of space in the heap, right? I know the heap is not going to be used, but it's memory that we would be using it necessarily. So we include instead inside of malloc a little guard to know whether or not we need to initialize our memory. So it's like lazy initialization, right? So lazy initialization. So we need to perform this lazy initialization the first time we call malloc. How do we know if we've called malloc before? Well, if we've called malloc before, then it means that we already have a root for the red black trio, or like we have a ghost node. And that ghost node is this arbitrary.block. So we see if we have not created any blocks of any sort or anything else, then, oh, well, let's see. Many languages. Oh, you also forgot Rust, C, alright, fine. Golang, Zig, Odin, and also Python. Pretty good. No JSTS there, nor Lua, and wait! JSTS, also Ruby. Okay, pretty interesting. No Ruby. Yeah. Can't forget that tournament. Idea what tournament? No Jai. I think Jai is closed access. It is, I'm just joking. Oh. Okay. So we start with this lazy initial. Guys, log in. Log in. Let's see. We start with this lazy Malloc, and what we do here. Okay, I was saying that I didn't want to look at the code because I don't want to like you know bias myself towards that. But I'm gonna just look at the previous code we had for the lazy initial allocation. I know. Don't worry. Don't worry. So we're gonna have padding, and that padding is gonna be okay. Align. Align what, brother? Oh, okay. Sure. So we just need to introduce some little padding, and we simply want the heap to start at an 8-byte aligned address. So that's what we're gonna do. Then over here, we're going to create a ghost node size. It's going to be equal to align the size of our block header plus the size of our block footer, I think is the right idea. Yeah. Because we're going to use this as a ghost node, and as such, we need this metadata to be present, since it's always going to be living inside the red black tree. Then we expand our heap by the amount of memory that we're going to need to allocate and put the padding and the ghost node. And then we need to just set up the ghost node, right? And we do that by telling the red black tree, this is the ghost node that you're going to get. So the ghost node is simply going to start wherever the padding starts. And then we set its left to be null, so that we can know for certain that there is no root. All right, I think that's it. Not gonna look at anything else. So, let's see. I do kind of want to try J. And I'm building Nialang, by the way. I mentioned custom C is the standard library. I was building this library for Nialang, but I realized that it is too hard to dev. So I switched to C++. That makes a lot of sense. Yeah, a standard library in C, completely, absolutely insane. Usually what I do is I like to take a look at the links you guys send me. Regular viewers of the channel know this. Unfortunately, if I open Firefox, my PC explodes. Because we just had that happen a few moments ago. I think we can take a look at it maybe tomorrow. You should send the link again tomorrow, and then we'll take a look at it. Your custom allocator was from the custom C. Damn. C is missing namespaces. Yeah. It's like one of the things that it's why I like C++ so much, because like it has, namespaces, you're able to like separate things easier. Same with the generics and stuff. So yeah. There's with all the features I want for a perfect low-level language. C++ has that, by the way. Anyways, to be fair, generics aren't very necessary either. Yeah, that's true. And I'm gonna start streaming this year, wantedly, since August as V2. Dude, that's crazy. Absolutely. Okay. Yeah, I wish it was a browser that used less but yeah. Everybody wishes browsers didn't use that much RAM. So perfect. Okay. Let's check our logic. So lazy initialization. So the first time they come Malloc, what do? We introduce the padding. there at the beginning, right? Thanks for the stream. We'll stop by again. Oh, bye, literally. Thank you so much for hanging around. And yeah, hopefully I'll be here. But yeah. So we're going to go through the lazy initialization logic. So first we introduce the padding so as to make the start of the heap be 8-byte aligned. Then we have the ghost node size, which will be the size of a ghost node that's going to point to where the red black tree is. We expand by that amount. We tell the red black tree, Mr. Red Black Tree, the ghost node you're looking for starts at heap pointer padding. And then we set its left to be a null pointer to signify to signal that there is no root yet. I think this is completely fine, right? Now, what do we need to do? We need to, let's see, a normal call to Malloc, right? We know the size that the user is giving us. Yeah. And so, what we want to do is we want to make this size be something compatible with our alignment. And so what I'm going to theorize is let's modify size to be the exact same thing we had before, you know? Align size of, and then the size of a UN32T plus the actual size minus the size of a UN32T. So this way, once again, right, we're able to get, you know, the extra bytes added to the end of the block. So now size is always going to be sort of cooperative with the purpose of having everything be aligned. And yeah, so now what we're going to do is Firefox is devved in C++. Oh, right, Penguin? Yeah. Size is equal to align, right? And then, so now size cooperates with our alignment. And now we don't need to align size anymore. Wherever we insert it, that thing is going to be 8-byte aligned, which is a great advantage. And this is one of the things we were missing before, where the footer would be like offset by a bunch of stuff and whatnot. Now we don't have to worry about that. I do want to include sort of to do reinstate metadata. So remember that free has the responsibility of reinstating the metadata once that block is free. It's a new responsibility that came by with the new design for memory blocks. So I just want to write it down so that we know that, like, oh yeah, this is something we needed to do. Remember. So once we calculate the size, it's gonna be aligned. It's gonna be great. It's gonna be awesome. The greatest size in the okay. What we're going to do is we need to find a block that's free and that can accommodate this request. Okay, so we're simply going to say, well, give me a free heap pointer to whichever block is free and can accommodate this request. And the way we do that is we tell the red black tree to find inside our red black tree something that has size this much. Perfect. And so now what we do is we say, well, if we actually found a free block, no heap pointer, then we're just going to serve that to the user. So to the user, we're just going to give the free block. Well, actually, no, we need to, you know, consider partition. So if the block is very big, we want to partition that block to give, you know, that little section to the user. As such, we can simply call partition if worth it, right? Partition if worth it. Partition if partition if worth it. Who are we going to partition? Well, we want to partition this free block that we just got, right? And not only that, but we want to accommodate for the size that the user needs. notice that this is going to provide us the new block that was created. So I'm going to call it right block. Okay. So this right block, needs to be added back into the red black tree because it's free now, right? So what we're going to do is we're going to say, well, rb_tree, and then we're going to insert into that red black tree. Which red black tree? Well, the one we save in a variable. We're going to insert the right block, right? And perfect, that should be it. Once that right block is inserted, only if right block is different from a no heap pointer, then we want to do things this way, right? Then we actually want to insert it. There's something here that we need to note, and it's the fact that this free block that we just obtained, we found that in the red black tree, but we have not yet removed it. And remember, we need to use partition with things that are not in the red black tree, because otherwise they get their state corrupted. So what we're going to do is we're going to say arbitrary remove the free block. Once we know that it's an actual block, which is the reason why I don't do it over here, right? So we want to remove from a red black tree the free block. Awesome. So now that that's done, we have considered the partition, we right block and everything, we add it back if that's the case, and everything should be sunshine and rainbows because we get to return the free block to the user. So what we do is we need to return a pointer, an actual pointer, not a heap pointer, because remember, our heap pointers are offsets. So we convert this to whatever the mem heap low is. So we grab the lowest byte of the heap, and then I think this returns a void, right? Void cell. Yeah. Okay. So I do need to change it to char. And then to it, we add the offset of a heap pointer, which leaves us in the free block. And we also need to add the, the offset from the size so that we land in user section. Perfect. Okay, we have it. Now that this is done, I think this is the entire logic for the case where we actually find a free block, right? We remove it from the red black tree. Since the red black tree is, the guy that like represents our free blocks, I think removal already sets its free and everything. So we should be fine. We partition if we're whoa, what happened? We partition only if it's worth it, right? If we actually partitioned, then we insert the remaining guy into a red black tree. If not, then we just don't do anything and we just return the free block. I think this is bulletproof. Oh wait, there's been a lot of chat messages. Let's see. Thanks for the stream. I know I have probably written more C++ than I have Rust. I've definitely written a lot of Rust. Programming in Rust requires that you must have colored hair. Don't blame me. I don't make the rules. The code makes the rules. What? Definitely one thing I want to learn is Rust. I've been interested by it. I've been introduced to the language before, sort of the theoretical, concept of it, of like how the borrow checker works and etc. But I feel like I would like to explore it a little bit more. But yeah, and see what it is like. Same for Zig. Zig is like one of those languages that I've been hearing a lot about and being sort of a direct competitor to C in Rust. Well, not direct, I guess, but yeah. Anyways, let's log in. So we have free block. Now, this is the case where we have there is no free block. Sad face. We have no blocks. What does that mean? That means that we need to expand the heap to create a new block, right? And for that reason, we are going to be involved with a few a few things, a few calculations. So it is likely and probable that the last block in our heap, current heap, is free, but just too short to accommodate for the user's request. And so we could reuse the space that this guy already has. The way we can do that is we can calculate how much space we would get from this and then only expand the heap by that amount. So something similar to that. There is sort of, yeah, I guess I'm just going to do it, right? Like, we just go to the last block, right? And that's going to be a heap pointer to the last block. Heap pointer to the last block. How you're going to, no, how do we access the last block? Well, fairly simple. We simply go to mem heap high. So we go to the last byte of the heap. And since the heap is going to be always a byte, it means that that last guy is going to be a footer. So now that we know that that is a footer, what we want to do is convert this to char star. Subtract from it. I guess rather than char star, I prefer a unit pointer. Because we're going to subtract from it. Well, I guess heap size, right? Mem heap size represents the heap pointer of that last block, -1. And this is the heap pointer of the last byte. And so now the thing we need to do is we need to go back by the amount of blocks or things that the footer has. So size of block footer. And I feel this is one of the problems that I was talking about earlier. And it's the fact that, notice, when we are here in our Excalibur, right? Suppose, ooh, okay, lots of arrows, I know. Let me just delete them. Lots of arrows, lots of arrows, lots of X's. Hello? There you go. So here, then we zoom in, we move, and then we delete. Perfect. Then we go back, then we enter here, then we delete all of this, then we delete all of that and that. No. Okay, perfect. So suppose this is the last block ever, right? This guy. Then what is going to happen is we store the is free information right next to, in the next block. Right? For that reason, we need to inspect the next block to know if we are free. The problem is the block at the end doesn't have a next block, which is a little bit of a problem, right? And not only that, to prevent that situation, we thought that including whether or not the current block is free would help, but that is not the case. Because over here, we only have access to the footer, right? So we actually don't really, right? We don't know whether or not it's free because we don't have access to the header. So I think we're going to have to modify things such that the current free is stored in the footer instead of the size header. That's going to be the harsh reality we're going to have to go through, unless one of you guys or somebody opposes to this and maybe has a better solution. Yeah. So let's think about it. So I think we're gonna have to include that in the footer, because if we don't include it in the footer, then it's gonna be absolutely impossible to work with. Yeah, I think that's effectively the only solution. Let me see. So Acid mem transmute. Odin look nice too. I want to try using Zig again. Made a game for a jam a bit of time ago. Oh, interesting. John Blow won't let us have Jenny. Zig has pretty recently banned AI contributors. I've made up a joke about this move. Zig. Okay. HCPRT. They have Game Jam this week. Oh, interesting. Why not build a custom J compiler? All right. Well, so I think with respect to this footer issue, we're definitely gonna have to use the footer. Yeah, I think that's an issue. That's an issue, and we need to fix it. Okay. Yeah. Oh, you spelled HPLTS. Oh, you're right. You're right. Sorry about that. Heap pointer type. Yeah, there you go. Perfect. Thank you. Earned Y collars? What do you mean? Collars? You mean like the collars from the editor? Oh. Yeah, IDs usually have collars. But yeah. So we have an issue. People, we have an issue. The town, reunite, please. Reunite. We have a problem. We have a problem. Convocation. Convocation. So we have a problem. As I explained before, we need to access the last block. And for that, what we do is we get here, right? Because the only way we know how to access the last block is by going to the last byte. And from the last byte, we need to tell whether or not that block is free. So we need to store a bit over there that determines whether or not the block is free, which damages or sort of kind of destroys the entire thing we were doing where we could save space with the size. Which is kind of annoying. I don't want that to happen because if we can just donate the entire size, that would be wonderful. Right? It would be perfect because then like alignment solves itself, right? Emergency meeting right. Okay. But yeah, no, if we donate the entirety of size, then alignment solves itself, right? Because to the user you could just provide all of that. This is a problem nonetheless that only occurs with the last block. And so we could consider simply adding a tiny piece of information at the end. That is, what's the issue? I got distracted. Brother, that's why we made the official meeting. That's why we made the meeting. That's the call. That's the call to the meeting. But yeah, no, I'm kidding. I don't know why I'm all over the place today. The issue is the following. So currently, when we're looking at over here, so if there is no free block, we're gonna want to span the heap, and we want to explore the optimization that we suggested last time, which was if the last block is free, then you want to reuse that space for the new block that's about to come into existence, right? For that reason, what we've, the problem we have here, and actually, let me write down something over here. Don't forget to update prev free on newly introduced block, which I think it's another issue we have with partition block. Yes. We have an issue here. To do, don't forget to set prev free for the newly inserted block. Anyways. Careful with the next neighbor because its metadata thinks left block. Left block is its left when right is the actual left. Okay, I'm writing cryptic messages, I know. Just let's keep it here. I need to come back to this. So the issue is, yeah, we when we're trying to expand the heap, we want that last free block to inherit that sort of expansion. So what we do is, well, we need to update the metadata of the last block. How do we get to the last block? Well, we go to the last byte, right? With the last byte, we look at the size and then we jump by that amount to get to the header. And then over here, we update the metadata and we say, oh, the size is now going to be this and this and this and that, right? The problem is if the last block is not free, how do we detect that? Because remember that size, like when this is allocated, all of this information is completely unreliable since it's part of the user's space. And so now we travel to the last byte and we don't have a bit to tell us whether or not that's free compared to what we've been doing previously. And that is because the last block does not have a next block. So nobody's storing their information. We also don't have a size. And so we're not able to travel back, but that's not a problem, right? Because if we had the bit, then we'd be able to say, okay, if it's allocated, then don't. If it's freed, then I know that size is present. And then I'll be able to travel back. But we don't have that bit at the footer. And that's like ruining everything. And what I was saying is, yes, we need that bit on the footer, which means that to the user, we can only provide the 3 extra bytes of size, which is very annoying because that starts, messing up with the alignment, I feel, although I'm not completely sure. Bit of last block is saved in first block like circular ring. Ooh. Okay, but now we have to introduce special cases. Um, Now we have to introduce special cases, which I guess is fine because we have a next block function, right? And since that next block function, yeah, we can just implement all the messy logic inside, and then it's gonna be hidden from us, and we don't have to worry about it. That is a great solution, I feel. Yeah, and that solves the entire problem, I suppose. Yeah, that sounds perfect. That sounds perfect. Because then it means, yeah, perfect. Thank you, Nick Bolsa, once again. Great contribution. Because then, if we update... Oh, Rune091, thank you for following. Yo, let's go. Same for Shaw63. Excellent. So, yeah, I think if we can simply update this Pad10, yo, all the people following, let's go. I think if we can just update this function to realize whether or not this block is the last block, then instead return the first block, we should be fine, I suppose. Let me think. Yeah, because then set is free inherits that capability because it just uses next block and it's hidden from it. So yeah, perfect. Yeah, let's do that. So how do we know whether or not this block is the last block? Well, fairly simple. We simply go and say, well, block, right? Block, the block pointer, plus the size of your size metadata, plus the size that your block is hosting. Actually, no. No. Because to access this function, we need to have a block pointer to the last block. And we don't have that. I guess we could just manually enter the first block, which I feel is what we are gonna end up doing. So let's see. If block plus size of this plus size of my actual block, this would land us in the first byte that's not part of my block. So I want to be the last byte of my block. If this thing is smaller than, well, no, greater or equal to the whole heap size, right? Mem heap size, then we know we're in the last block. So if the last byte of my block, which is this is the last byte, is greater or equal to the heap size, then it means that we're in trouble. Because then that lands outside. Oh, sorry. Wait. I think if I just remove this -1, we're gonna be fine. Yeah. So if the block pointer is that, then we add 1. We're gonna end up with the heap size. Yeah. Okay, perfect. So if that's the case, then we're going to say, well, your next block is actually not that guy. It's, oh my god, it's the ghost node. It's the ghost node. So the ghost node is like storing 0 information, right? And thus, what we can do is just use the ghost node, right? Yeah, right? Wait, Nick Vols, you say block equals memlow. Memlow would be pointing at the first byte of the heap. So that would refer to not the last block, but instead the first one. I guess that's like the other case we would need to figure out, but yeah. How? What do you mean? Yeah, because this block pointer, I think we're fine. Then once this happens, we need to return the ghost node, which is living at the first address of the heap. Now remember that the heap doesn't really start at like heap pointer 0. It starts at padding heap pointer. So to the heap, we add like the padding at the beginning, if you remember correctly. And that padding is something we need to keep track of to know where the first block is, to know where the ghost node is. I think, oh, actually, no, we do know where the ghost node is because in the initial allocation, we set the padding to be arbitrary.block. So then we can just save it there. So we just return, right, arbitrary.block. That's its next block. Okay, so if we are the last block, then we say the next block is the red light tree block. And that's the guy that's going to store our information. Absolute cinema. Yeah, so since the ghost node is a normal node, we can just live with it. This is awesome. Like everything is clicking into place in such a beautiful way. Like I don't even know how to express it. Don't forget to update the pre-stream. Where were we? I think we're here. Yeah, there you go. So the last block is gonna be this guy, right? And the thing is, we cannot use the function we just created, but we do know whether or not that last block is free. So here, right? Bool is last block free. And the answer is gonna be for rb3.block, right? We need to access its prev free. So we're going to access. Oh, okay. I guess that's like one of the disadvantages of of the way we did this, because in every single function we're assuming that like we know what the block pointer is to the point to the blocks in a memory, and here we don't. So we need to just take a look at something like prev free, right? Sort of like access that blocks prev free for the arbitrary block. And I guess we can just allow that, mainly because we can simply set it as a getter and not create a setter for it. Pref free, you just pass me the pointer to the block that you want to take a look at, and then I'm going to give to you from the header of this block, we access the space, the previous free, and the free, those guys, and then we simply collect the guy that lives in 0B10, right? The second to last least significant block, bit. There you go. And this should be block prev free, and block is free. It should already be possible to access. So great. I think I'm just gonna change. No, actually, let's not change anything. Block prev free of this guy, and then we're gonna know if the last block is free by looking at the first block's previous free. Perfect. That sounds awesome. So now what we're going to say is, well, if that last block is free, then I want to merge it with whatever I have to expand the heap by. So there's a fundamental question here, and it's how much do I have to expand the heap by, right? So expansion size. Right? How much do we need to expand it by? We need to expand it by either, so the maximum between two things, right? The expansion factor times the amount of heap that we have. This is just sort of like the heuristic, right? Sort of when you need to expand a vector, right? You need to add another element, and you, instead of adding the amount of space that's exactly needed for it, you simply double the size of the vector. Here is something similar that's happening, right? If we need to expand the heap, rather than accommodate it for that exact size, we simply expand it by the extension factor, right? But it could be the case that we need to expand the heap by a big amount, which means that the expansion factor would not be able to cover that much. And so we just pick the max between the two, the max between that expansion factor and the size that we actually need, right? And not only the size, but size of u in 32t, because we're going to need a new block, right? We're going to need a new block. Now, there is a consideration we need to make. We need to say, well, if the last block is free, then I can reuse part of that space. I can say, well, the expansion size actually needs to be smaller because you can already use my metadata and the size that I have. So we just subtract from it the size of a UN32T, which should be the size metadata of that last block, plus the last block size, which which we should be able to access. So last block size, and then I should be able to take a look at the footer. Okay. Not this way. Instead, it should be something like bk footer, and then I should access the last block. Okay, we just have a problem with interface. So, sorry about that. Put this guy here. So what's going on is the following. We calculate the expansion size. How much do we need to expand the heap by? After that, we say, well, is the last block free? If the last block is not free, then we simply, we just expand by whatever this is. If it is free, then we want to reuse that space. So we want to, from the expansion size, remove the stuff that we can already reuse. And what can we reuse? Well, from that last block, we can reuse everything. So its size header, but we also can reuse whatever, the little space that it had reserved for the user. How long is that space? Well, we would need to know the size of the block, but we currently just have a pointer to its last byte, and we don't have a pointer back. So what we need to do is a bit of a complicated thing. So last block size, it's going to be a UN32T, and this is going to be the last block size. And how is it going to be expressed? Well, it's going to be, if I'm currently in the last byte, I want to travel 3 more bytes to the left, right? So I'm going to take a look at the last byte, mem heap high. And then I go 3 bytes to the left, and think of this as my footer by converting it back to a block footer pointer. And then I access it, its size member, right? Hopefully. I think you just need to close it in one more parenthesis. Everything should be all right. Perfect. So we get the last block size. The reason why we cannot call footer is that block footer expects a block pointer, right? So if it expects a block pointer, we would need to know what the block pointer for the last block is, but we just don't know that, right? So we do that, and then we add to it the last block size, which is pretty good, right? We just have it. There. That's the amount of things we can reuse. You need to remove it from the tree, change its size, and partition it. Yes. That's indeed what we had over here. We actually, like, our code, it would make like, oh, right, grab the last block, change its header, change the size, change everything, remove it from the tree, then partition it. Like, yeah, I have that in mind. I just don't want to look at the code because that makes us biased towards maybe some of the errors we had before. So here, if this is the last block, if the last block is free, then we're gonna grab the last block size. You could do this. Then the expansion size, we know what it's going to be. And then at the end, we simply need to expand our memory by that much. So we create S break, and then we add expansion size, right? We say expand my heap by this amount. I think that's correct, question mark? Expansion size, yeah. Now we have a little bit of a thing where if the last block is free, so I'm gonna write it in comments first, right? So here it's like if last block is free, then like change last block to adopt extra space, right? If not, then what we need to do is convert the extra space into if not, we need to convert the extra space into what? Into convert the extra space into a free block. Dude, come on. Okay, that means that over here, not only do we need to get the max of this, right? But we need to also include a third thing, which means this would be the max of this guy. And the minimum amount of bytes needed for a block to be valid, right? Because we still need to have space to store this kind of metadata, because it's going to be a free block, potentially. And so now what we can do is we can say, well, if the last block is free, right, we are going to be able to do this thing. So if the last block is free, we change the last block to adopt the extra space. So what we need to do is I'm going to create like a little variable here, something called, the heap pointer to the last block. And then if the last block is free, we're going to be able to populate this with an actual last block. If the last block is free, we're going to be able to point out, so this is the size, which means that the last block's heap pointer is going to be equal to what? Well, to the heap size minus 1, which points to the last byte, and then that minus the whole, let's see, the whole size information. Okay, I see. Minus the last block size. So we just skip the user section, and then we go back the size of a unit entity. Right? And so now, let's see, if we are in the byte after the last one, which would be heap size. Let me have this in parallel here. If we imagine that we just have, four guys, the mem heap size would put us here. Then we subtract the last block size, which is, say, I don't know, 12. So then we go 1, each of these is 4 bytes, 2, and then, ooh. Well, okay, so first we have to go 3 bytes to the left, then it would be like 1, 2, 3, yeah. And then we reduce by the header size, and then we end up in the header. Okay, so we end up always at the beginning of the header, right? And so now we can take this last block, and this will be the heap pointer for it. And then that's it. Yeah, last block size. Perfect. So now what we're going to do is we're going to say, well, if the last block is free, then we want to, once again, adopt that extra space that we just got from expanding the heap. The way we're going to do that is relatively simple. So we remove from the tree, we're going to remove that last block because its size is about to change. Last block, hello? Oh yeah, remove from the writeback tree the last block. And by this point in time, we need to assert that last block is indeed different from a null heap pointer. Perfect. So we're going to remove it. Once we have removed it, we are able to modify it. So how are we going to modify? Well, we're going to set its size to something completely different, right? It would need to be, bk size, and then we set it for last block to whatever my previous size was, plus the extra added space. So I think we still need to store that information somewhere, and I think we can just do it here, right? There's a unit32t last block size, and then just leave it there. Last block size, and then this guy redefines it, and now. Yeah, so BK size has one argument, yeah. BK set size, yeah. Because we cannot access, I mean, we could just create another variable here, which is like size, just like get the size before we modify it. Well, I guess I don't need to do all of that, right? I guess we just, yeah. So I just say BK set size of who? Well, of the last block. And thank you, Penguin Operator, for the comment. Yeah, so we set the size of the last block to be this block size. It's already included there. Plus, and then we're going to have the expansion size, right? How much size was added at the end? Life is so cool when you don't have to worry about the footer. I feel that was one of the most helpful comments I could have received from Nick Folsen. We set the size, then we have the last block, then that last block size, it's just going to be the previous size it had, plus whatever the heap was expanded by. That makes sense, right? Speak now or forever hold your peace, or where it's at. And yeah, I think we're good to go. So is there anything else we need to update from this block? Nothing else, right? We already removed it from the tree. The is free information is still there since it's the same block. Yeah, I think we're good. We're good to go. And so now what we do is we simply give to the user that last block, right? We don't give it directly the last block. We give him a char star that starts at mem heap low and then builds itself up to the point where the last block is, and then adds to it the size of a UA32T pointer, right? So that should be able to, yeah, perfect. So we start from the initial byte of the heap, then the last block is gonna take us to where the last block is, and then we skip the size section because that should be metadata, and then the user can use the rest. Perfect. So that's if the last block is free. If it is not free, right, if not, then we need to convert the extra space into a free block. So we simply, I guess that this one is even simpler. This one's even simpler. Well, actually, we could just do this, right? Yeah. So this wouldn't even be needed, right? We just put it up here. Then this assertion is, of course, not going to be violated by any means. And so now we don't need this branch. And then that's it. Right? Oh, but that's only if there is a last block. If there is no last block, then last block becomes something. Nick Wilson says petition expanded block before returning it to the user. Oh, you're right, because we could expand by an expansion factor rather than the exact amount. So, I guess, yeah. Yeah. So, okay. Let me see. This is if the last block is free, then we want to do all of this. But then, whenever we're setting the size, we're doing it for the last block, and that's not what we want. What we want to say is, well, here we have the memory break, and if the last block was not free, then we need to make the new expanded space to be a huge free block. So the way we can do that is we can set the size of whatever that was. I think mem sbreak returns a pointer to, yeah, the start address of the new area. So we can simply say something like heap pointer t new area, or like expanded area is equal to this thing, right? Converted to a char star pointer minus the mem heap low. Also converted to, well, I guess rather than char star, I prefer you in PTRT. PTRT? And then same over here. Right, so we take the first address there and then subtract it from the lowest byte in the heap, and then that's going to give us the heap pointer to where the expanded area begins. So if the last one is not free, then we're going to think of expanded area as a block, right? We're just going to make last block be equal to expanded area, right? And so now we can simply say, independent of what happens, I feel it just gets confusing if I rename the variables. Let's just do them one by one. So here, if the last block is free, then all we need to do is remove it from the tree, right? Set its size to be this plus the expansion size, and then just return that with the caveat of the fact that we need to partition. So how would we partition? Let's see. If the last block is free, grab its size, we get the last block, we subtract from the expansion size, we remove it from the tree so as to make it, not free. And then we set that block's size to be whatever it had before plus the expansion of the heap. And once that has taken place, we want to see, okay, maybe the block it's pretty big to satisfy the user's request. So now we try to partition it, and we apply the same sort of principles that we've been looking at before, where we simply say, once we've set the size, we say right block is going to be equal to partition if worth it. Who do we want to partition? Well, we want to partition the last block. And we want to partition for a size that is needed to allocate the user's request. If it was worthy of being partitioned, that is, if there's now a new block on the right, then we need to add that right block to our red-black tree. And we need to do all sorts of stuff. So arbitrary insert this red block, right? And there's nothing else we need to do. Oh yeah, arbitrary and then right block. Perfect, which I think is indeed the way we've been doing it before. Like here, we remove it, we grab the right block, yeah, and then if it's no, yeah, then we return the actual thing. So now we return the mem heap low and then plus the last block and then plus that. So we should be fine with this. Now the problem is, what happens if the last block isn't free? Or we need to convert that expanded area into a block. So convert expanded area into a block. So the expanded block, let's call it that. It's gonna start there. And what we're gonna want to do is we're gonna want to set its size, set the size of this expanded block to be equal to what? Well, to be equal to the expansion size minus the size of whatever is holding the size data, which is a UN32. Yeah, perfect. And so now, oh, new message in chat. Odoswi, hi, hello, welcome to the chat. Are you Jewish? No, I'm not Jewish. But yeah, I don't know. Let's see. We have the block set size, right? So, Odoswi, we are coding a memory allocator from scratch in C, as the title says, and we're currently writing Malloc, right? So let's see. All right. So we have the block set size, right? We expand the block. We set its size to be, or to interpret the expanded area as a block. And I think we don't need to do anything else, right? Because once we interpret that as a block, yeah, we just apply the exact same reasoning. We say, well, if this thing, blah, 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 then return. Yeah, so I'm going to copy and paste this code. And then we're going to simplify it because I think we can just merge the two branches to make the code simpler and be able to work with it. So now we partition it with it, not the lax block, but the expanded block. And then after that, we return, right? So I feel this is the complete logic of our malloc function. Chat, is this it? So we're gonna want to merge these two things. So, because notice that both of them are doing the same work by like partitioning and then returning in the end. So what we can do is simple and easy. If the last block is free, then we're gonna do all of this work. If not, then we want to take the expanded block and interpret it as the last block. If not, I'm gonna take the last block and interpret it as that. So now I'm gonna take this, I'm gonna say last block, set it to the expansion size and everything, and then here, convert expanded area into a block, the last block by definition. Perfect. And so now after that, we're able to reuse this piece of code over here, which is simply in charge of partitioning the block and making sure that everything is in the right place. Awesome. Renato Peixe, 1982, Shakira. Yes! Yeah, Shakira, Coleman singer, absolutely incredible. Great representation of the country. Love Shakira. But yeah, let's see. So does this make sense to you guys? Is it good question? Because give me 2 minutes. Okay, I'll be back. Think about the code while I'm out. You know, take a look at it, and if you notice something weird, let me know. All right. Hello. Wait, when I remove my earbuds. Anyways, let's see. Are the flags retaining the correct settings after each manipulation? Yes, that is one of the things that I was worried about. I think the only thing we need to take a look at is the partition function, which is why I included those cryptic comments at the beginning. Because notice, so when we enter malloc, right, lazy initialization doesn't really move anything. It doesn't do much. So let's focus on this. and we get the size, get the free block. So our red black tree doesn't modify the metadata to a point that it could get it corrupt, right? We verify that find actually gives you the right metadata, save for remove. Partition, if worth it, is the one that could be a culprit, and in fact is a culprit when it comes to corrupting the flags. So insert, not gonna do anything. Expansion size, everything, this is just a getter. This, the blocks are not getting modified anywhere that could corrupt them. In the sense that arbitrary remove, we know doesn't corrupt the flags. This doesn't corrupt the flags and doesn't, change things around in some weird way. My neighbor to the right is still my neighbor, and my neighbor to the left is still my neighbor when I set the size. So none of these things should change. Now, wait, where is the mem s break? What? Why is it here? Oh, yeah. Okay. So, yeah. When I performed the merging of the two, I did like some weird thing. Let me just go back to the simpler times. Yeah, I think this is it. Yeah, here. So, okay. Notice that, okay, if the last block is free, then we get its size to get the pointer. Then we have the expansion size, but we never expand. And we definitely need to do that. So it should be more like this. Right, we have the red black tree remove. We remove it from the red black tree. We expand by the actual, by what we actually need, which is the expansion size. I realize now that this expansion size has to be aligned. So we also need to align that. Let's see, the Geeko 1. Hello, seems like the algo got me a gem. Saba 7 Alcair. What is Alcair? Anyways, welcome the Geeko 1 to the chat. The algo got you a gem. What do you mean by the algo got you a gem? What is do you mean the algorithm of the memory allocator? I'm not sure. Wait, if you can clarify what do you mean? I'm so sorry. I don't understand, but let me know. Expression must have integral type. Brother, what do you mean? Operands to binary expression, double and int. Are we doing this guy is the culprit. He is guilty. Okay. One U and 32T, we convert this to whatever this thing is. Hi. Okay, that should be it. Yo, let's go. The Geeko 1, it's like good morning in Arabic. I thought you speak Arabic. The of Twitch got me a joke. Oh. Hello. Welcome. No, actually don't speak Arabic. I'm from Colombia, South America. Yeah, I know the name is a little misleading. I also don't have any sort of Arabic ascendance, which is kind of strange, right? It's kind of weird to have like a name that's an Arab name and then not have anything related to it. It's just that my father really liked the name, so he decided to name it Sharif. So I'm so sorry I didn't know what you were saying, but oh, I see the algorithm of Twitch. You got your James. Okay, perfect. No, that's awesome. Yeah, we're coding here on memory allocator. I think we're close to the end of writing Malloc. very, very close. So we're currently seeing what happens when you expand the heap to have more blocks. Um, and that's exactly what you see on screen right now. So we're calculating the expansion size by how much we need to expand the heap. Then we take a look at whether or not the last block is free. Then we actually, we see, well, if it's free, then get its pointer. And then from the expansion size that you're going to need, just reduce it by the amount that's already there, because we can reuse that space and then remove the last block from the red black tree. After that, expand. And once you expand, we need to do Defliner, don't worry about it. It is a nice name. Oh, thank you so much. But yeah, no, I like my name a lot. But yeah, it's interesting. You give very leavened look. Interesting. Interesting. Yeah, I don't know. We, you know, maybe there's some Arab ascendants somewhere. Maybe not that I'm aware of. Maybe I have like a great grandfather. Because I do remember there was a lot of migration from that region to Colombia, but it was quite a while ago, especially from Turkish people. But yeah, and some Lebanese too. So yeah, I don't know. We'll see. Means the honor roll. Yeah, that's great. Yeah. I was aware of that one. I had a friend that told me like, dude, your name in there means the honor roll. It was very interesting. I don't know. So yeah, we have here. We need to expand the heap. So we expand the heap over here, and then if the last block is free, then we need to play with the last block by setting its size to the new thing and then returning whatever this is. If the last block is not free, then we need to convert that expanded area into a block, right? So we find the expanded block, we set its size to what it needs to be, and then we also partition again, right? So I think the confusion, because this piece of code is like exactly the same, the confusion was that for some reason I did this, but then didn't do anything else. So I think like if I do else and then include the exact same code that we have here, except for the repetition, then we can just get away with it, right? Because we have a heap pointer of the expanded block, and this, rather than be an expanded block, can just be the last block. So convert expanded area into a block, which in fact is the last block by definition. This is the comment we had before, definition. And now what we're going to do is we're going to say, well, grab this heap pointer and then return. Yeah, I think that's it, right? Yeah, it's just that this thing changes from expanded block to last block. I think that's it. Okay. Go to Cheeseburgers. Thank you so much for following. Let's see. Learners Mivana. Any new block need... Wait. Oh, no, also, do you speak Arabic? Damn. Any new block needs to set its flags too, not only its size. Yes, that's true. But since we are giving this block to the user, we don't need to set its flags, right? Oh, well, no, actually. Whoa! What did I just say, bro? Okay, never mind. Whoa! I said the most stupid thing a human being can say. Yeah, no, of course we need to do that. Yeah. The last block already has its flags in point, right? The thing is going to be with this guy, right? Once we convert it to a block, we set its size, and then we also need to set the fact that it's free. We need to. Anyways, last block we need to set it to true because it's the new expanded area. And okay, we also need to set the previous free to point to the last block. Okay, this is really annoying. Well, oh, happy Trennies, thank you for following. Yo, we have guys. It's a let's see. Anyone that programs at C89, C99 deserves a follow. C89 can rise up. In your sinky SE live. Okay, well, brother. I feel it would be a little bit of a betrayal if I told you that I usually code in C++ and that this is my first time coding in C for a formal project. But I like C++, I do have to say. But I feel this is my ritual of conversion, changing to C for the first time. Seriously, no, I had coded in C before, but it is a bit of a more serious project. So let's take a look at this because we have a little bit of a conundrum because now since this block just came into existence, we need to set its flags, right? We need to set its flag as Nick also pointed out, and for that it means that we need to set the is previous free. But we don't have a setter for that precisely because I didn't want to exhibit that interface so that we wouldn't modify it. I mean, I guess we're just gonna be careful about it. Separate free. Anyways, you pointed to the block that we want, and then the new value for pref free. And what we're going to do is we're gonna enter the header of that block, and then we're gonna access SPFF, and you're gonna set so pref3 is the second to last least significant bit. Now we need to end this with the negation of that, and then make bk header at block be an O of pref3, just shift it to one to the left. Yeah. Okay, I think we're good to go, I suppose. Right? Perfect. So what we need to do here is we need to say, well, set this blocks free to true and set the previous block, so bk set previous free of the last block to be, to be is last block free. The naming is a little confusing. I acknowledge that. But I think maybe we can do something like this. He pointed to expanded block is equal to this, which is equal to that. Does C allow this? I think so. And then for the sake of naming, we can change this to expanded block so that we don't confuse the two notions. Yeah. Perfect. Okay. JLM03, welcome to the channel. Yo. Yeah, thank you for following. And let's see. Guys, we have 71 followers. Can you believe that? 72 now. 72 followers, actually. That's like absolutely insane. Right? Like, what? 2 weeks ago, we had how many? 10 followers? No. 2 weeks ago, no. 1 week ago, we had 10 followers. If I remember correctly. Is this wow? Anyways, I digress. At the beginning is semicolon, sorry, because you're doing giga chats. Brother. Let's see. So here we're doing maybe heap size, right? Expansion size, yes. arbitrary remove. Okay, so here are we doing the right things to set the flags? So we convert the expanded area into a block. We set its size. We set its being free. Then we set the previous to be free, right? Depending on whether or not that last block is free. And then after that, we, yeah, I think we're good to go. The flags are now set because the only flag we care about is previous free. The current free and all of that doesn't really matter because I mean, it's like current free is what we as the block use, but we are not going to be interested in that. So instead yeah, okay, so everything's set. Color we don't care about, left we don't care about, right we don't care about, parent we don't care about. We don't really care that much about current free, but we still set it. And we do care about previous free, which we set. Last block free still has the information of its previous free, so that should be completely fine. We're simply expanding it, so we don't need to modify its flags. Right block, I think this is the correct approach. Now. I think this is better now. Sorry guys, something happened. Let's see. Because so while growth, yeah, it absolutely insane. Like I don't know. So, anyways, if you switch to C++, all will be gone. Huh? No, no. C++ is C++ is it's like I don't know what the feeling of being a parent is, but it's usually said that parents always love their children. No, it's like even if you have a child that is usually very prolific, they do well in school, but they have a little bit of annoying things about them. It's still your child, and like you're still gonna love him a lot. I feel that is my relation with C++. To put it in a very abstract concept, you know. Anyways, I digress once again. Man. Drainiard, welcome to the stream and thank you very much for following. So yeah. Um let's see. Okay. So I think this is the logic for C++ is not my child, right? It's Bjorn Strip's child, but it is that feeling where you're like, there are some things that are wrong with you, but like, I've been with you all the way, and like, it's like, you know, yeah, whatever. Anyway, or the other way around. Am I C++ child? Who knows? Anyways, we have completed, I believe. Of course, there's going to be a lot of errors here, but this is definitely better than what we had before, because before we were not thinking about the alignment on the user section, we were not thinking about the memory heap and all of that. We're not thinking about the flags. Now I think we are a little bit more on our feet. We oh wait, this thing is about to die. 9%. Give me 1 second. I'm gonna pull out the other one. And I'm gonna put this back into the recharge case. Oh. Oh, hello? Oh yeah. Okay, perfect. So. What I was saying. If there's no free block, this is the most important section. Pay attention. Pay attention, people. Okay. We calculate the expansion size. Then we say, is the last block free? Right? We take a look at that. Then, if it is, we grab that last block and we say, expansion size, you're allowed to reuse the space that block was occupying. Then we remove the last block from the tree. After that, we expand the heap. And if the last block was free, we simply set its size to be the new thing, right? We sort of make it occupy the expanded size. Otherwise, we're going to convert the expanded area into a block, right? So what we're going to do is we're going to say, if the last block wasn't free, it means that my new block starts exactly where the new area is. So I grab the expanded block, I make it be the last block, right? And there's a problem here. This is a bug. Yeah, last block. And then this should refer to last block. So what I was intending was something more like, you know, see, because the naming here is a little bit important since, okay, we convert the expanded area into a block. So now the last block is not the previous block, but the new expanded area. So we make the last block be the actual last block, which is the expanded area. Then we set the size of that last block to be this. We set the fact that it is free right now. We set the fact that the previous one is free, right? So the last block, I guess I don't need to know this. I just say false, right? Because if we are in this else, then we definitely know that the last block being free is false. So then that's it. Yeah. Okay, that's perfect. Yeah, I think we're fine. I think we're totally fine. Perfect, I think. Yeah, I think we're good. So now we set the pref free, and then after that's done, we have the last block, be it the new area or what previously was the last block. We don't care. We just know that it is already set. Everything is clean and tidy. So what we do is we partition it in case it's really big, and then return it. So I think this is exactly what we want. Oh wait, I see the kbps are. Oh no, it's becoming crazy again. Guys, let me know if the stream is lagging because I see it. Like I see the kbps are going up and down. Oh, it seems like it's stabilized. Anyways, no, it didn't stabilize. No, why is it going away? Yeah, I think we can apply the same hack. If I hide my camera, it like stabilizes, I think. Yes, it stabilizes. And then if I turn it back on, it's gonna keep being stable. So let's wait for 2 minutes and 1 minute or something like that. And then actually no, I'm too impatient. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we turn it back on, and then it should stabilize again. Yo, let's go. It's stabilized. Okay, that's great. So, as I was saying, we are looking here at the Malloc code, and I think there's nothing else to look at. The only thing, as I mentioned before, is this partition function. So, whenever we partition a block, notice the comments, the cryptic comments down left, which is like, don't forget to set pref free for the newly inserted block. So notice that when we partition, we bring a new block into existence, which is this guy, the right block. So we need to update that block's flags too. It's also the fact that if, I think it's better if we just pull up the Scali draw. Yeah, here you go. So suppose we have, right, this is our memory, okay? And suppose we have some, ouch, no, ouch, there you go. We have a 52 long block, and maybe there's like this block over here that is only 12 bytes long. Oh, sorry about that. It's only 12 bytes long, 12. And then there's this one that's 40 bytes long, right? Suppose we want to partition this 40 byte long block. What we do is we find, say, to accommodate for a request of 12 or something like that, we partition at some point in time, then we change this to be whatever the number is, in this case 16 probably, right? 16, and then 16, and then make the remaining thing accommodate to that. So it would be something more like 24. Right? These are, of course, numbers, just bear with me. What is that? This guy is now brought into existence. So its previous free needs to add to tell us whether or not the previous block, which is this one, is free. But this guy to make it point with its previous free variable. So that's the information that we need to consider. And as such, we need to set over here. So one thing I'm gonna do is I just want to create a heap pointer for the right block. I know. Unnecessary variables, yes, but it's just for the sake of of code reliability, right? So, and then here I just return the pointer to the right block. Perfect. So what we do now is we are going to say, well, for the right block, so for the normal block, nothing needs to change, right? Nothing needs to change. It's previous free, it still has the same previous neighbor. It still has the current free. Nothing has changed, everything is fine. But for the right one, the right needs a little bit more attention, right? So the right one needs, let me change this for that. Oh, sorry. The right one needs to have its size set, but not only that, it needs to realize that it is free currently. Well, not it's not free, right? Set the is free to be a right block and then put it to false. Yes, because we assert that every single block that's here should not. Actually, no, we petition for a reason. Well, I guess that doesn't matter, right? Because we told the user this thing. I mean, actually, this function corrupts the arbitrary metadata as well as current free. Perfect. So now we set not the size but the pref free to be its brother. So we set the pref free to be whether or not the block that we return is free, which should be false, right? Or I guess, I mean, block is free of block, but this assertion over here guarantees that's going to be false. So that for the sake of readability, it's better to just do it this way. These functions are going to be inlined either way, so I think it's fine. Yeah. Oh, Nick Volsa, is it like raining and snowing where you are? Huh? Or do you mean that the stream is frozen? By the way, if you learn Rust, you're going to have to change your username from SharifSegfaults to Sharif Lifetime Doesn't Live Long Enough. Yeah, wait, that's true. I guess it's something I didn't consider, right? I stopped being SharifSegfaults because I cannot segfault anymore. That's one of the more common mistakes I make when when creating programs and all of that, which is the reason of the name. I think most of the C and C++ developers, a segfault is like the error that everyone commits all the time. So yeah, if I start learning Rust, that's gonna go away. existential crisis, I suppose. But yeah, okay, we set the size, we set the previous to be free. I think we're fine, right? Now that we set the previous to be free, we're good to go. And oh, the next neighbor. The next neighbor. Yeah. So now we set the prev3. Actually, no, we don't need to really worry about that next neighbor. Because we can just pk set is free. So currently, I mean, we assume the right block to be free. So I'm just gonna make it true, right? This is not gonna be that helpful. It's completely fine because either way, once they call partition block, they're going to reinsert this block into the red-black tree, which means that it's going to be set it's free to true. And remember that is set is free also updates the header of the next block. And so we will be completely fine. Either way, it's good to include it there. And I think this is it. Right? So I think we don't need these comments anymore. This is the end. Oh, this is the end. Do 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 do. Los denomina stolen in the sky fall. Anyways, yeah, I think it's it. This is it. There's definitely some mistakes somewhere, but we will test that. And I do have to announce I'm a tiny bit over the stream's length. Yeah, I was supposed to be at the office at 9 a.m. Anyways, that doesn't matter. Everything for the stream, and of course, I mean, I'm not gonna rob my company, and I'm going to work, extra hours in the night just to compensate. But yeah, I think because of that, I do need to go right now. But thank you very much, guys. So I think one of the last things we can do is simply commit this. So git commit feat initial malloc rewrite not tested. Now I'm just gonna push this. Awesome. All right. Okay. Perfect. Yeah, it was just 5 hours. Anyways, that's concerning. Well, yeah, we've been 5 hours in the stream. Can you imagine? Next stream tomorrow. I'm not gonna link you guys. So I mean, I do have to admit, there's an exception today because we got a raid from Jasper from which was like absolutely insane, completely unexpected, and I was so happy that I was like, nah, screw this, because I was planning on ending this stream at 10 a.m., which is what I hope to aim at. But then like Jasper raided, I wasn't like, it was impossible to let go of the stream. I was really happy and really wanted to end the Malloc function. So yeah. Thank you very much, guys. Follow to know when we go live. But I think that now I want to have a constant schedule. Stream starts at 7:15 a.m. PST. I think I created the schedule in the Twitch channel, so take a look at that. And we end at 10 a.m. hopefully every day, because once again, I have to, responsibilities and stuff. So, yeah. So all of that, and I'll see you guys tomorrow where we're going to test our implementation of Malloc. Okay? All right. Bye-bye. See you guys. Ooh. All right, bye-bye.